When we hear the word diamond, we think of something rare, brilliant, and small enough to fit in jewelry. But what if I told you there might be an entire planet made of this material? That's exactly the hypothesis that emerged in 2012 when astronomers analyzed the exoplanet 55 Cancri E, located about 40 light-years away. The idea was bold. This world could have large portions of its interior crystallized into diamond. Since then, this planet has become something of a celebrity in scientific circles. 55 Cancri E looks nothing like Earth. It orbits so close to its star that it completes a year in just 18 hours. Imagine that, a planet where the entire calendar fits into less than one Earth day. This proximity causes surface temperatures to exceed 3,600 degrees Fahrenheit or 2,000 degrees Celsius, hot enough to turn any rock into an ocean of lava. Additionally, it's probably tidally locked, meaning one side of the planet always faces the star while the other remains in eternal darkness. The clue that led to the diamond planet idea came from the system's star. The ratio of carbon to oxygen seemed much higher than what we're used to, and that changes everything. Here on Earth, oxygen dominates and combines with silicon and iron to form minerals that make up the crust and mantle. In a carbon-rich system, the formation process is different. What remains in large quantities tends to crystallize into graphite and, under enormous pressures, into diamond. It's worth noting that this planet wouldn't be a gleaming sphere, sparkling in space like a jewel. What scientists imagine is something more discreet, a dark crust, perhaps covered by graphite and carbonaceous minerals, hiding vast layers of diamond inside. The sparkle would be buried under miles of rock. Still, in terms of scale, we're talking about something incomparable. Diamonds in quantities sufficient to make all Earth seem like an insignificant pebble. This hypothesis, even without definitive confirmation, has already changed how we think about exoplanets. For a long time, the standard model was to imagine rocky worlds as different versions of Earth. But 55 Cancri E showed that chemistry can generate completely new results. Carbon worlds, water worlds, iron worlds. The diversity is much greater than we supposed. And what would it be like to live on a diamond planet? For starters, the heat would be unbearable. But in a hypothetical scenario where this planet was in a habitable zone, things would be very different. Diamond has peculiar physical properties, like extremely high thermal conductivity. This means internal heat would escape in ways different from Earth, altering geological activity. Instead of tectonic plates as we know them, there might be giant eruptions and unstable magma flows. From an astrobiology perspective, this type of planet opens many questions. If carbon worlds existed in more tranquil orbits, could life emerge there? Perhaps not water and silicate-based life like ours, but exotic forms adapted to environments dominated by liquid hydrocarbons and different minerals. This is the kind of question that keeps scientists alert to every new piece of data. Another interesting thing is that 55 Cancri E isn't the only suspect. The Kepler telescope and other observatories have already identified systems with high carbon ratios, suggesting that similar planets might be relatively common. If true, diamond worlds wouldn't be cosmic rarities, but just another category of planets among many others. Despite this, scientists are cautious. Later studies questioned the star's carbon ratio and suggested that perhaps the planet isn't as rich in this element as initially imagined. Science works this way. An initial hypothesis draws attention, new data arrives, and gradually the picture is adjusted. Even if 55 Cancri E isn't literally a diamond planet, the idea opened an entire field of research. Another fascinating detail is that more recent observations showed the planet isn't static. It emits heat irregularly, suggesting extreme volcanic activity. This indicates its surface is in constant transformation, perhaps with lava oceans that move and evaporate rapidly. If diamonds really exist there, they're buried under this chaotic environment, inaccessible even to futuristic space probes. And of course, the idea also captured popular imagination. When the news broke, newspapers and magazines worldwide rushed to talk about the Diamond Planet. It didn't take long for works of fiction and even discussions about space mining to enter the scene. After all, if it were ever possible to extract diamonds from such a world, the concept of value here on Earth would change completely. But this is more of a cultural than scientific exercise. The real value for astronomers is understanding the limits of planetary formation. Planets like 55 Cancri E are natural laboratories, showing how variations in a star's chemistry can give rise to bodies with unexpected characteristics. This expands our theories and helps build a more complete vision of how the universe manufactures planets. The story of 55 Cancri E is also a perfect example of how science evolves rapidly. In just a few decades, we went from knowing no planets outside the solar system to debating whether some of them could be made of diamond. This speed of progress is impressive and shows how each discovery redefines what we thought possible. In the future, more powerful telescopes may confirm or definitively rule out this hypothesis. The James Webb is already providing clues about exoplanet atmospheres and compositions, and its successors will have even more precision. Perhaps in a few decades, we can say with certainty whether diamond worlds are common or just rare cases. Sirius B, the super-dense white dwarf. When we look at the night sky, few stars command as much attention as Sirius. It's simply the brightest point in the celestial sphere, visible to the naked eye from virtually anywhere on Earth. But what not everyone knows is that Sirius isn't alone. In fact, it's part of a binary system. The star we see easily, called Sirius A, has a much less obvious companion, known as Sirius B. And it's precisely this companion that holds one of the most fascinating stories in modern astronomy. Sirius B is a white dwarf, meaning the remnant core of a star that has gone through all active phases of nuclear fusion. It can no longer produce energy the same way as the Sun, but still shines intensely due to residual heat it carries since its collapse. To the human eye, hidden by the blinding brilliance of its larger neighbor, it's invisible without powerful telescopes. Even so, its existence forever changed how we understand stellar fate. The discovery of Sirius B dates back to the 19th century. Astronomer Friedrich Bessel noticed that Sirius A showed subtle oscillations in its apparent motion across the sky. These irregularities could only be explained by the presence of an invisible companion, pulling it gravitationally. It was a brilliant deduction for the time, a demonstration of how Newtonian physics could reveal the presence of celestial bodies no one had ever seen directly. Decades later, more powerful telescopes confirmed the prediction. There was Sirius B, a tiny and extremely dense star. To understand how special it is, a comparison helps. Sirius B is approximately the same size as Earth in diameter, something around 7,500 miles. But despite this reduced size, its mass is almost equal to the Sun's. This means the density of its matter is unimaginable to us. A single sugar cube made from Sirius B's substance would weigh tons on Earth's scale. This characteristic made the scientific community, still in the early 20th century, seek explanations in a new frontier of physics, quantum mechanics. What keeps a white dwarf stable is no longer nuclear fusion, but a principle called electron degeneracy pressure. In simple terms, the electrons in its atoms are compressed to such a point that quantum physics laws prevent them from occupying the same energy states. This microscopic, almost counterintuitive resistance is sufficient to balance the immense gravitational force trying to crush the star even more. The result is a compact and stable object that slowly cools over billions of years. Sirius B, being one of the closest white dwarfs to Earth, became a natural laboratory for astronomy. By studying its mass, size, and light spectrum, scientists could test fundamental theoretical predictions. It was thanks to observations of this type that confirmation of the so-called Chandrasekhar limit emerged. A white dwarf can only exist if it has up to 1.4 times the Sun's mass. Above that, quantum pressure isn't sufficient to contain it, and the star's fate is much more dramatic. It collapses into a neutron star or even the black hole. Another notable aspect of Sirius B is its surface temperature. Today it's around 45,000 degrees Fahrenheit, 25,000 degrees Celsius. This heat, however, doesn't come from nuclear reactions, but from energy stored in its previous collapse. Over time, it will continue cooling until it becomes a black dwarf, an object that, in theory, no longer emits visible light. But the universe is too young for any white dwarf to have reached this stage yet. The study of Sirius B was also crucial in confirming another important physics prediction: gravitational redshift. Since a white dwarf's gravity is enormous, even radiation emitted from its surface loses energy when escaping, shifting to longer wavelengths. This effect, called gravitational redshift, was measured in Sirius B and served as one of the first observational confirmations of Einstein's general relativity. In other words, besides being a curious object in itself, Sirius B was key in validating fundamental theories about the universe. Historically, this star has always played a prominent role. Sirius A, the main star, was revered by ancient civilizations, including the Egyptians, who associated its appearance in the sky with the Nile's flood cycle. They didn't know, of course, that hidden beside that intense light was an invisible, compact, and exotic companion. This later discovery shows how even the most familiar objects in the sky can hide surprising secrets. Another curiosity is that at some point, Sirius B was very different. Before becoming a white dwarf, it was a massive star, brighter even than Sirius A is today. During its red giant phase, it expanded its outer layers and then expelled them into space, leaving only the compressed core. This reminds us that stars, like living beings, have life cycles with birth, evolution, and end. Sirius B represents one of these final stages, making it a glimpse into the future of stars like our Sun. This detail is especially fascinating because it gives us a mirror for what will happen to our system. In about 5 billion years, the Sun will also collapse and leave behind a white dwarf. By studying Sirius B, we can anticipate how this process will be, what impacts it will have on the solar system, and how the surrounding space will be marked by this type of transformation. The relative proximity of Sirius B also facilitates obtaining precise data. By measuring its orbit around Sirius A, astronomers managed to calculate stellar masses with previously impossible precision. These measurements helped consolidate stellar evolution models we use today to understand everything from birth to death of stars on different scales. In this sense, Sirius B isn't just an exotic object, it's a reference point that helped build the very structure of modern astrophysics. And we can't forget to mention the absurd gravitational force it exerts. Gravity on Sirius B's surface is about 350,000 times more intense than Earth's. This means that if you could stand on its surface, which isn't possible of course, you would instantly weigh hundreds of thousands of times more than here. No known material could resist such pressure. It's a practical demonstration of how physics in white dwarfs inhabit completely different territory from what we experience daily. The brightness of Sirius B, even being such a small star, continues to be impressive. Although outshined by Sirius A when seen from Earth, in infrared and other wavelengths, it's possible to study it more clearly. These studies reveal how it's slowly cooling, step after step, following the destiny of all white dwarfs. This cosmic countdown is valuable to astronomers because it allows using white dwarfs as natural clocks, helping estimate the age of entire stellar populations. Another interesting point is the historical interaction between Sirius A and B. When Sirius B went through its red giant phase, Part of its material was probably transferred to its companion. These mass transfer episodes are common in binary systems and can have profound effects on each star's evolution. Today, Sirius A continues strong in its stable star life, but the presence of the white dwarf beside it is a reminder that it, too, will follow this destiny in a few billion years. In cultural terms, Sirius B also awakened imagination among people outside science. It appears in esoteric discussions, modern mythologies, and even controversial theories, precisely because its invisible existence for centuries seemed mysterious. But in the scientific field, the mystery converted into solid data and a very rich study object that helped prove fundamental laws of physics. The future of Sirius B is predictable in general terms. It will continue cooling until it becomes a black dwarf. This will take trillions of years, much longer than the universe's current age. That is, we are still seeing this object in an intermediate phase of its long trajectory. Until then, it will continue serving as a milestone for our studies, and as an example of how relatively common stars can have such extreme destinies. Sirius B, therefore, isn't just a footnote beside the brightest star in the sky. It's one of the most important objects ever discovered for astronomy. Its absurd density, its stellar transformation history, and the role it played in validating physical theories make it a true cosmic laboratory. And at the same time, it's a reminder that the Sun itself will one day have the same end, making the study of these stars not only fascinating, but also deeply relevant to understanding our cosmic future. Oumuamua, the interstellar visitor. In October 2017, a completely unexpected object entered the list of modern astronomy's most intriguing discoveries. A telescope in Hawaii, Pan-STARRS 1, detected a point of light moving unusually relative to background stars. Calculations showed it wasn't another common asteroid or comet from the solar system. Its trajectory was hyperbolic, meaning it wasn't bound to the Sun. It came from outside. Named Oumuamua, a Hawaiian word that can be translated as messenger from afar arriving first, the object was the first confirmed interstellar visitor. It was no longer just a theoretical possibility that rocks and fragments could wander between stars. It was concrete evidence. For the first time, we faced a piece of another stellar system crossing our cosmic backyard. Right from the start, what drew most attention was its shape. Brightness variations indicated the object rotated irregularly, like a poorly balanced top. The amplitude of these variations suggested it had an extremely elongated form, perhaps 10 times longer than wide. For comparison, most asteroids known in the solar system rarely exceed a 3-to-1 ratio between length and width. Oumuamua looked like a cosmic needle, but it wasn't just the shape that intrigued. Unlike comets, no visible tails or gas jets were observed that could explain its slight acceleration when passing by the Sun. This raised various hypotheses. Perhaps its surface was covered by a crust that prevented volatile release, or perhaps it was expelling gases so discreetly that instruments couldn't detect them. Either way, the object didn't behave exactly as we expected. The reddish color also drew attention. It's typical of bodies rich in complex organic compounds, exposed for long periods to cosmic radiation. This detail fits well with the idea that Oumuamua wandered through interstellar space for millions or even billions of years before accidentally crossing our path. It was, in a sense, a natural capsule, bringing with it chemical records of processes happening in other regions of the galaxy. The biggest challenge was trying to understand where it came from. Reconstructing its trajectory, astronomers concluded it entered the solar system from the approximate direction of the star Vega in the constellation Lyra. But this doesn't mean it departed there. During the immense time it traveled through space, stars changed position, systems moved, and its origin remains uncertain. It was likely ejected by gravitational interactions in a binary system or during planet formation around some distant star. The fact that we detected an interstellar object for the first time reinforces the idea that they must be common. Every stellar system, during its formation, must launch thousands of fragments into interstellar space. Taking this on a galactic scale means the Milky Way is full of objects like Oumuamua, silent and invisible, crossing the void between stars. The difference is that this was the first we managed to catch at the exact moment of passage. The discovery, of course, generated intense debates. Some scientists suggested alternative hypotheses to explain its unusual characteristics. One of the most publicized was that perhaps we weren't facing a natural rock, but something artificial, like a solar sail created by an advanced civilization. This hypothesis gained space in the media, but most of the scientific community remains cautious. There's no concrete evidence to support this idea. Still, the simple fact that we needed to consider this possibility shows how much Oumuamua departed from patterns. The peculiar acceleration behavior is a good example. Normally, comets accelerate when near the Sun because they release gases and dust, but in Oumuamua's case, this release wasn't observed. One suggested explanation is that its surface could be covered by an insulating layer that hid sublimation. Another idea is that it was composed of solid hydrogen ice, which would sublimate rapidly without leaving visible traces. None of the hypotheses were confirmed, but each opens new research lines. Besides its science, the object also marked astronomy as a cultural event. For the first time, we had the concrete sensation that pieces of other worlds really pass through here, reminding us that the solar system isn't isolated. This perception reinforced the idea that the galaxy is dynamic, with materials constantly exchanged between systems. Even Earth's formation may have been influenced by such fragments from distant regions. Observationally, the biggest challenge was time. When detected, Oumuamua was already moving away at high speed, leaving the solar system at about 59,000 miles per hour. This gave astronomers only a few weeks to collect data before it became invisible even to the largest telescopes. In no time, it was already lost in darkness, making any detailed follow-up impossible. This limitation generated frustration, but also motivation. Today, projects like the Vera Rubin Observatory and automated monitoring networks are being prepared precisely to quickly identify future interstellar visitors. The idea is not to miss the opportunity to study them more closely, perhaps even with rapid space missions that could intercept and analyze one of these objects in situ. Oumuamua also brought reflections on how we classify objects. It didn't fit well in any traditional category. It wasn't exactly a comet, but also didn't have the typical appearance of an asteroid. This indefinition led the International Astronomical Union to create a new designation for this type of visitor, I for interstellar. Thus, its official name became 1I Oumuamua, the first catalogued interstellar object. Another fascinating aspect is thinking about this body's travel time. If it really spent millions of years wandering through space, then it already existed long before humans emerged. When crossing our solar system, it brought with it a story dating back to cosmic eras, a narrative we'll never completely know. For scientists, every detail observed in its reflected light is a fragmented clue to this distant past. Even with all limitations, Oumuamua was a milestone. It showed our observational capacity reached a level where we can detect not only what forms near us, but also visitors from other corners of the galaxy. It was a reminder that space is much more interconnected than we imagined. After it, in 2019, another interstellar visitor was identified, Comet 2I Borisov. Unlike Oumuamua, Borisov behaved like a classic comet with visible tail and composition easier to analyze. This helped reinforce the idea that interstellar objects really circulate in large numbers throughout the galaxy. But Oumuamua remains special because it was first and because it still maintains unanswered enigmas today. The future reserves new attempts to find objects like it. Some scientists even speculate about missions capable of pursuing Oumuamua, although its current velocity makes this extremely unlikely with current technology. The most realistic approach is waiting for the next visitor and being ready to study it in detail, learning as much as possible before it disappears again into darkness. Sagittarius A star, the black hole at the center of the Milky Way. If you could travel to the heart of our galaxy, you would find a landscape that seems straight out of science fiction. At the center of the Milky Way, 26,000 light-years from Earth, exists an object that cannot be seen directly, but whose presence dominates everything around it. It's Sagittarius A star, the supermassive black hole that keeps the galactic structure united. Invisible by nature, it only betrays its existence through the colossal effects of its gravity. The discovery story of Sagittarius A star is relatively recent. In the 1970s, radio telescopes detected a compact and extremely energetic source at the Milky Way's nucleus. This point shone in radio waves as if it were a cosmic antenna, but no optical telescope could see it. Over time, it became clear there was something extremely massive there, concentrated in a minuscule region on an astronomical scale. Confirmation came at the turn of the century. Astronomers observed, with almost superhuman patience, the movement of stars orbiting the galactic center. Some completed trajectories in just a few decades, as if they were dancing in tight circles around an invisible point. The only possible explanation was the presence of an object with millions of times the Sun's mass compressed into an area smaller than Mercury's orbit. And this object could only be a black hole, not just any black hole, but a supermassive one, with something around 4 million solar masses. It's difficult to imagine what this means in terms of density and gravitational force. Think of the Sun, now multiply its mass by 4 million. Then squeeze all of this into a sphere whose diameter is comparable to a small planet's orbit. This is Sagittarius A star. The curious thing is that, despite all this, it's currently in a dormant state. Unlike active black holes that devour matter at an accelerated pace and shine like radiation beacons, our galaxy center seems relatively calm. This doesn't mean it's a tranquil place, just that the black hole isn't currently swallowing large amounts of gas and dust. Still, occasional sudden energy bursts are detected, indicating that pieces of matter fall toward it and are heated to absurd temperatures before crossing the event horizon. One of the most striking images in recent astronomy came in 2022, when the Event Horizon Telescope revealed the first direct photograph of Sagittarius A star. Of course, it's not a conventional photo. What we saw was radiation brightness emitted by particles accelerated around the event horizon, forming a diffuse ring of light around a central shadow. This portrait, comparable to the one obtained of M87, was almost poetic proof that black holes aren't just equations on a blackboard, but real objects, palpable in observational data. The region around Sagittarius A star is a natural laboratory for extreme physics. Stars orbiting close to it, like the famous star S2, follow trajectories that allow measuring effects predicted by Einstein's general relativity. When S2 completed its maximum approach in 2018, astronomers could register a deviation in its light's wavelength caused by the black hole's intense gravity. It was another direct confirmation of how space and time distort before such colossal masses. But the Milky Way's central black hole doesn't only influence nearby stars, it plays a vital role in the galaxy's architecture itself. Its presence stabilizes the nucleus and regulates, in a way, star formation in that region. Studies suggest past activity explosions in Sagittarius A** may have shaped gigantic structures like the so-called Fermi bubbles, immense formations extending tens of thousands of light-years above and below the galactic disk. Despite being central to the Milky Way, Sagittarius A* represents no immediate danger to us. At 26,000 light-years away, its gravitational influence doesn't reach Earth. Our solar system orbits tranquilly in the galaxy's periphery, taking hundreds of millions of years to complete one full revolution around this nucleus. What happens there, in the center, is for us distant theater, fascinating to watch, but safe at a distance. Still, the idea that there's a colossal black hole anchoring our galaxy has profound implications. It's a reminder that supermassive black holes seem to be a common feature of galaxies. We don't know exactly how they form, whether they arise from giant star collapse in the universe's first generations, or slowly feed until reaching these absurd masses. But whatever the origin, they seem present in practically all large galaxies we've observed. Sagittarius A* also challenges our intuition because it's simultaneously invisible and incredibly influential. Nothing can escape its event horizon, not even light. Still, we can see its effects in various ways, in nearby star orbits, in radiation emission from accelerated particles, in the impact its activity leaves recorded in larger galactic structures. It's like trying to study a main actor who never appears on stage, but leaves marks in every detail of the story. One question that intrigues scientists is why our central black hole is so quiet compared to others. Active galaxies, like quasars, have nuclei that shine brighter than all their stars combined, precisely because their black holes are in intense feeding phases. Sagittarius A* seems to have been on a diet for a long time. Perhaps it's just a temporary phase, perhaps it's its nature, but this relative tranquility gives us the rare chance to study a supermassive black hole closely, without the noise of constant explosions. Observations of Sagittarius A* also have practical applications for astrophysics. How matter behaves around its event horizon serves as a test for theories trying to unify general relativity with quantum physics. The superheated plasma spinning around it, emitting radio waves, is an environment we can't reproduce in any terrestrial laboratory. There, nature offers us a real scenario where fundamental laws are pushed to the limit. The black hole at the Milky Way center also helps us understand the galaxy's long-term evolution. It probably went through periods of much more intense activity and may return to energy bursts in the future. There are indications that, on scales of millions of years, gas clouds and stellar clusters are pulled to its region, reigniting its veracity. When this happens, Sagittarius A* can release jets of radiation and particles that alter the entire galactic nucleus dynamics. The complexity of the environment around Sagittarius A* is such that we're still only scratching the surface. Combining observations from different telescopes, from infrared to radio, scientists manage to assemble a kind of composite portrait of what happens there. But each advance brings new questions. Exactly how does matter organize when falling into the black hole? How does the magnetic field influence radiation emission? Are there regular periods of activity, or is everything chaotic and unpredictable? For the general public, Sagittarius A* is usually remembered as an invisible monster at the heart of the galaxy. This image is impactful, but also limited. It's not just a matter devourer, it's also an essential element of cosmic structure. Without such an immense center of gravity, the Milky Way might not have the shape we know. In this sense, the black hole is less a threat and more a structural pillar, silently sustaining the dance of hundreds of billions of stars. Looking to the future, increasingly sophisticated missions will continue monitoring Sagittarius A*. The Event Horizon Telescope, for example, should produce even sharper images as new antennas are added to the network. Meanwhile, space telescopes like the James Webb help map surrounding gas and dust, offering new clues about how the black hole interacts with its environment. Studying Sagittarius A* is ultimately studying our own galaxy. It's the Milky Way's heart, the point around which everything revolves, the invisible axis that keeps united the structure that houses our Sun, our planets, and, ultimately, ourselves. Hot Jupiter WASP-12b, the planet being devoured by its star. There are planets that challenge our imagination by what they are, and there are those that impress by what's happening to them right now. WASP-12b falls into this second category. It's a doomed planet, in the full process of destruction, being slowly swallowed by its own star. When we think of alien worlds, we imagine exotic scenarios, but rarely remember there are also planets in agony. WASP-12b is classified as a hot Jupiter, meaning a gas giant similar to Jupiter, but orbiting absurdly close to its star. To get an idea, it completes one orbit in just 1.1 Earth days. This means its orbital distance is so short that the star's gravity deforms it, stretching it into an ellipsoidal shape. Instead of being a perfect sphere, it's more like a football. This proximity generates a fatal phenomenon. The star's gravitational force is slowly tearing away its atmosphere, sucking gases from the planet like a cosmic straw. Astronomers call this mass transfer. Part of WASP-12b's atmosphere forms a hot ring around the star, a clear sign the planet is being torn apart. It's like watching an inevitable death sentence in real time. The heat on its surface is another extreme characteristic. Average temperatures reach over 4,500 degrees Fahrenheit, 2,500 degrees Celsius, hot enough to vaporize metals. Any solid material known on Earth would be melted or destroyed in seconds. The atmosphere, expanded by this heat, becomes even more vulnerable to the star's gravitational pull. The result is a self-destructive cycle. The more the atmosphere heats up, the more it inflates, and the more easily it's stripped away. A curious detail is that WASP-12b is no longer in the stability zone that many exoplanets manage to maintain. It orbits within the so-called Roche limit, a region where the star's gravity overcomes the planet's gravitational cohesion. In other words, tidal forces are so intense, the planet is literally being ripped apart. This process happens slowly on human scale, but in cosmic terms it's fast. In a few million years, WASP-12b might simply cease to exist as a planet. Observations made with the Hubble Space Telescope were crucial for understanding this scenario. When starlight passes through the planet's atmosphere during a transit, astronomers can identify chemical signatures, and what they saw was an extended cloud of hydrogen, helium, and carbon escaping into space. It's as if the planet were permanently surrounded by an invisible comet tail, undetectable to the naked eye, but detectable at the right wavelengths. This type of planet shows something important. Giant world lifespans aren't as stable as they might seem. Jupiter, here in our solar system, is in a safe orbit, 484 miles from the Sun. But if it were 100 times closer, it would have the same fate as WASP-12b. This comparison makes clear how crucial orbital position is for a planet's survival. WASP-12b's ellipsoidal shape also stands out as one of the first times we could directly observe gravitational deformation of an exoplanet. This isn't just geometric curiosity. The distortion alters how it distributes heat and even how it rotates around itself. In such extreme worlds, physics doesn't behave like in textbook examples. Every detail of orbit and gravity has direct impact on structure. The escaping atmosphere forms a kind of material current between planet and star. This current resembles the process in binary systems when one star sucks matter from its companion. The difference is that here, the victim isn't another star, but a planet. This parallel made some astronomers describe WASP-12b as a reverse vampire planet. Instead of sucking, it's the one being sucked until it disappears. Another interesting factor is the color this planet would probably have for a nearby observer. Models suggest its superheated atmosphere absorbs most of the light it receives, making it one of the darkest exoplanets ever detected. WASP-12b reflects less than 10% of stellar light, roughly equivalent to an asphalt ball floating beside a cosmic furnace. This dark aspect fits well with its tragic destiny. In terms of scale, what's happening to WASP-12b also has value for us. The mass transfer process shows how gravitational interaction can reshape entire systems. Giant planets, which once seemed unshakable, can have brief existences when they get too close to their stars. This helps explain why many hot Jupiters seem rare. They simply don't last long. Another detail that draws attention is how this planet became so close to its star. The most accepted hypothesis is that it migrated inward through the system over billions of years, disturbed by gravitational interactions with other planets. When it got too close, there was no going back. The orbit is in decay, and the end is just a matter of time. In cosmic terms, it's like watching a slow dance toward destruction. The fact that we can observe this process is a rare privilege. Most exoplanets we know are in stable phases of their orbits. WASP-12b shows us a transitional moment, a midpoint between formation and disappearance. This type of observation is crucial because it gives clues about how planetary systems evolve and change over billions of years. For some astronomers, WASP-12b is almost like a warning. It shows what happens when cosmic forces go out of balance. It doesn't require imagining catastrophic collisions or supernova explosions. Sometimes a planet's destruction happens silently, through invisible forces that work slowly until nothing remains. The spectacle isn't explosive, but it's equally inevitable. And it's precisely this inevitability that gives WASP-12b a special place among discovered exoplanets. It's not just strange for its temperatures or short orbit, but because it's living its final chapters as a planet. With each orbit around its star, a bit more of its atmosphere is lost, making clear we're witnessing a disintegration process on a cosmic scale. In the future, the star that today devours WASP-12b might end up surrounded by a debris disk, remains of the planet that no longer exists. This material might form new structures, might be swallowed completely. For us, this cycle helps remember that nothing in the universe is permanent, not even worlds the size of Jupiter. Cosmic strings, space-time defects. When we think of structures in the universe, we normally remember galaxies, stars, or nebulae. But there's a much stranger hypothesis, almost invisible and still unconfirmed, the so-called cosmic strings. Unlike any solid object we can imagine, they would be flaws in space-time's fabric itself, something closer to a defect in a mesh that stretched too quickly than a body made of matter. This idea alone is enough to intrigue physicists and cosmologists for decades. The notion of cosmic strings arose in the 1970s, when scientists began exploring consequences of quantum field theories applied to the primordial universe. During the Big Bang, while the cosmos expanded and cooled, different fundamental forces underwent phase transitions, something comparable to water freezing into ice. In this process, irregularities could have emerged, small scars in space-time. Cosmic strings would be precisely this type of scar, extending across unimaginable distances. Imagine pulling a knitted fabric and noticing that in some points, the thread tangled wrongly, creating an irregular line cutting through the pattern. This metaphor is frequently used to explain cosmic strings. They wouldn't be structures made of atoms as we know them, but energy concentrations embedded in the universe since its first instance. Therefore, they don't emit light and don't reflect radiation directly. Detecting them is thus an enormous challenge. The theoretical properties of cosmic strings are impressive. They could have densities so extreme that a single mile would contain more mass than Mount Everest. This density translates to intense gravity, capable of distorting space around them. In practical terms, a cosmic string passing near Earth would alter satellite orbits and could even provoke earthquakes induced by sudden gravitational force. Fortunately, there are no indications that any has ever crossed our path. Another striking characteristic is the speed at which these strings could move. Theories suggest they would travel through space at velocities close to light speed, forming complex networks that cross, stretch, and even break. When a piece of cosmic string breaks, it could release enormous amounts of energy in the form of gravitational waves. This detail is especially important because it offers an indirect detection method. By observing space for anomalous gravitational waves, we might find clues to their existence. There are also bolder hypotheses. Some physicists have raised the possibility that cosmic strings could connect to black holes, or even form structures resembling wormholes. These ideas are still in the speculative field, but they reinforce the almost fantastic dimension of the concept. We're not talking about rocks or gas, but entities that exist because the universe itself went through a turbulent formation process. For a while, it was believed that cosmic strings could explain galaxy distribution in the cosmos. The idea was that these filaments, by exerting their colossal gravity, would have helped organize matter right after the Big Bang, serving as invisible scaffolds for large structure formation. Later, observations of the cosmic microwave background showed that matter distribution could be explained without needing strings. Still, the hypothesis wasn't abandoned, it just changed function, from central explanation to complementary possibility. One problem in confirming them is that if they exist, they must be extremely rare or nearly imperceptible. And even a string crossing our galaxy wouldn't be easy to observe directly. What scientists seek are secondary effects, gravitational distortions in distant galaxies, anomalous signals in cosmic background maps, or gravitational waves that don't correspond to black hole or neutron star collisions. It's cosmic detective work, where traces are worth more than direct evidence. Some calculations suggest that, if detected, cosmic strings could have microscopic widths, smaller than a proton, but extending millions of light-years. This paradoxical combination, thin as almost nothing, but long as the universe itself, makes their nature even more difficult to conceive. It's not a material rope we could touch, but a line of pure energy, invisible and almost indestructible. The energy contained in a single string would be so absurd that if we could extract a fragment of just a few miles, it would release more energy than all Earth's nuclear bombs combined. This shows how much they are not just exotic, but potentially dangerous. Of course, this is just a theoretical hypothesis. So far, no string has been observed, and there are no indications they're in our immediate vicinity. Despite all the difficulty in finding them, the search continues. Observatories like LIGO and Virgo, which have already detected gravitational waves from cosmic collisions, are also used to look for signals that could be attributed to cosmic strings. So far, nothing has been conclusively detected, but in science, absence of evidence isn't evidence of absence. The universe is too vast to rule out possibilities based only on what our instruments can see today. Another line of investigation involves gravitational lenses. If a cosmic string crossed the line of sight between us and a distant galaxy, its gravity could deform light characteristically, creating duplicate or distorted images. Searching for this type of signature in telescope data is another way to try identifying these objects. But since the phenomenon is subtle, we're still not sure if any candidate has been found. The theory of cosmic strings also connects to more speculative areas of physics, like string theories. Some models suggest these defects could be macroscopic manifestations of quantum phenomena occurring in the universe's first instance. Others consider they might just be mathematical artifacts without real existence. It's an open field where hypotheses coexist with concrete data scarcity. Even with so much uncertainty, the simple possibility that cosmic strings exist maintains many researchers' interest. They would represent not just an exotic discovery, but a key to better understanding how the universe evolved since its first seconds. Detecting them would be like finding fossils of events occurring right after the Big Bang, recorded not in rocks, but in space-time's fabric. It's curious to think that in a universe full of visible and tangible things like planets, stars, and nebulae, one of the future's greatest discoveries might come from something we can't see directly. If cosmic strings are out there, spread in some corner of the cosmos, their discrete nature is what makes them even more intriguing. After all, they would be silent memories of a forming universe, stretched like energy lines crossing darkness. The search for these strings also illustrates how science advances through bold possibilities. Many ideas that are now part of consensus, like black hole existence or accelerated universe expansion, were once seen as unlikely speculations. Perhaps cosmic strings follow this same path, from risky hypothesis to revolutionary discovery. Or perhaps they remain as an elegant theory without real manifestation. In both cases, they already fulfill their role, forcing science to think beyond what's visible. The most fascinating thing is that if a cosmic string were detected, it would change not just our view of cosmology, but also of fundamental physics. This is because its existence would be directly linked to phase transitions occurring at the universe's beginning, at energies much greater than we can recreate in laboratories. They would, in essence, be messages from the cosmos's infancy, preserved for billions of years. Until we have concrete evidence, cosmic strings remain as one of the strangest objects ever proposed by physics. They are not made of ordinary matter, don't shine, and don't fit any traditional category. They are, in theory, flaws in space itself. And this strangeness is precisely what makes them so fascinating. In the universe, not everything that exists needs to be made of atoms. Oort Cloud, the solar system's invisible frontier. When we think of the solar system, the common image is of planets orbiting the sun, with their moons, asteroids, and perhaps the Kuiper belt where Pluto resides. But all of this, however large it seems, is still just the center of the stage. If we moved away thousands of times the distance between Earth and the Sun, we would reach territory we've never seen directly, but which almost all astronomers believe exists, the Oort Cloud. Unlike the asteroid belt, which is a ring, or the Kuiper belt, which forms a more flattened edge, the Oort Cloud is thought to be an immense sphere. It would be like an ice and rock bubble surrounding the entire solar system, extending to almost 1 light-year away. At this distance, the Sun's gravity no longer reigns alone. Neighboring stars and even the Milky Way's gravitational field begin competing for this invisible frontier. Curiously, we've never seen this cloud directly. No telescope can distinguish its object so distant. Everything we know comes from clues left by long-period comets. They appear suddenly, coming from any direction, with orbits that can take millions of years to complete. It was by observing this behavior that, in the 1950s, astronomer Jan Oort suggested the existence of this cosmic reservoir. The scale is almost impossible to imagine. Pluto, which seems to be at the solar system's edge, is only 50 astronomical units from the Sun. The Oort Cloud possibly begins at 2,000 units and could reach 100,000. For comparison, Voyager 1, our most distant probe, has been traveling for almost 50 years and hasn't even scratched the edge of this hypothetical region. The blocks that would form the cloud are, in theory, frozen and rocky, pieces remnants from the solar system's infancy. During giant planet formation, billions of small bodies were hurled outward. Some escaped forever, but others remained trapped in enormous orbits, too far to return, but still bound to the Sun. They would form this almost inexhaustible comet stockpile. And it's precisely from there that many of the most spectacular visitors we have seen in the sky come. Halley, Hale-Bopp, and many other comets probably originated in this distant cloud. When a neighboring star passes relatively close, or when the galaxy's gravitational tide disturbs their orbits, some of these bodies are launched toward the Sun. It's only at this moment they become visible to us, with their bright tails cutting through the night sky. Without this cloud, there would be no way to explain the quantity of comets we still find. If we only depended on those we know more closely, this stock would have run out long ago. The Oort Cloud functions as a great cosmic warehouse, replenishing the inventory of visitors that illuminate the interior of the solar system. Another striking detail is the shape. While almost everything orbits in the same plane, like a disk, comets from the Oort Cloud appear from completely random angles. This only makes sense if the reservoir is spherical, distributing objects in all directions. It's as if we were at the center of an invisible bubble, and occasionally some dark fragment of this bubble would light up when approaching the Sun. What's impressive is that, even with trillions of possible bodies out there, space is so vast they would be incredibly far from each other. It wouldn't be a dense cloud, but an almost empty region where each frozen object could be millions of miles from the next. It's a counterintuitive image, lots of material, but spread so thinly that the whole becomes almost untouchable. And despite never having seen it directly, this cloud's influence on Earth is real. Many scientists believe that part of the water and organic molecules that allowed life's emergence reached here through comets, some from precisely this region. On the other hand, some remember that large cometary impacts could also have caused mass extinctions. In both cases, the Oort Cloud would be indirectly linked to life's history on our planet. Actually exploring it is still beyond our reach. The distance is so absurd that any probe would take tens of thousands of years to get there. Therefore, the most ambitious plans today focus only on probing intermediate regions between the Kuiper Belt and the cloud's beginning. That would already be a huge advance. An intriguing aspect is that the Oort Cloud might not be exclusive to the Sun. It might mix with neighboring stars' clouds, so some objects change owners over time. This opens the possibility that certain comets we observe formed in other stellar systems and somehow were captured by ours. In this sense, some visitors would be, without us realizing, interstellar messengers. The hypothesis also connects to another much-discussed idea, Planet 9. Some strange orbits of trans-Neptunian objects suggest the presence of a still undiscovered planet, hundreds of astronomical units from the Sun. If it exists, it could influence the Oort Cloud's edge behavior, disturbing orbits and launching comets inward. The solar system's frontier in this case would be even more dynamic and full of surprises. Computer simulations of planetary formation suggest part of this cloud might be made of imported objects. In the stellar cluster where the Sun was born, billions of years ago, it was common for young stars to exchange fragments with each other. This means the Oort Cloud might be a mosaic, a collection of pieces not just from the Sun, but also from other sister stars from our distant past. Even without direct observation, scientific consensus about its existence is strong. Comet trajectories fit perfectly into this model. It's one of those cases where we don't see the structure but can map its shadows. And the more comets we study, the more solid the idea becomes that the Oort Cloud is real, even remaining invisible. This region also carries practical implications. Although rare, encounters with comets from this cloud can be dangerous for Earth. These are objects arriving at extremely high speeds and can be large enough to cause catastrophes. That's why telescopes sweep the sky searching for new comets. They're the messengers escaping this distant reservoir. It's impressive to think that the solar system's outermost part, which we've never seen, might have shaped so much of our history. It provided ingredients for life, but also brought risks of destruction. The Oort Cloud is, in this sense, an example of how distant frontiers can have direct effects on the small world we inhabit. Galaxies without dark matter. Enigmas challenging the standard model of cosmology. When we talk about dark matter, we're referring to one of modern physics' greatest enigmas. Despite never being detected directly, for decades we've known it seems to be everywhere. Galaxy rotation curves, stellar cluster movements, and even how cosmic background radiation distributes in the universe point to the existence of invisible mass corresponding to about 85% of all matter. It's as if most of the cosmos were made of something that doesn't emit, absorb, or reflect light, but whose gravity keeps structures united. In this scenario, any news about a galaxy without dark matter sounds almost impossible. That's exactly what happened in 2018 when a team led by Peter von Dockum from Yale University announced the discovery of an anomalous galaxy called NGC 1052 DF2, located approximately 65 million light-years from Earth. Scientists observed the movement of globular clusters within this galaxy and concluded their velocity was compatible only with the visible mass of stars. In other words, there was no sign of dark matter sustaining the structure. The idea was received with both enthusiasm and skepticism because it challenged part of cosmology's standard model. The method used to detect dark matter presence in galaxies isn't visual but dynamic. Under normal conditions, stars in outer regions should move slower than those in the center. But what astronomers find is that, in almost all galaxies, stars maintain high and stable velocities, even at the edges, something that can only be explained by the extra gravity of a large amount of invisible matter. This is how the dark matter hypothesis was consolidated. But in the case of NGC 1052 DF2, velocities were too low, meaning its mass was explained only by visible stars. This result was so unexpected that it immediately raised alternative hypotheses. Some astronomers suggested the galaxy wasn't as distant as it seemed. If it were actually closer to Earth, the calculated mass would be smaller and the dark matter deficit would disappear. Others questioned whether measurements could have suffered statistical errors due to the small number of globular clusters used in analysis. But as more observations were made with the Hubble telescope and other instruments, evidence that it was a real galaxy with low density and no dark matter strengthened. NGC 1052 DF2 belongs to a class known as ultra-diffuse galaxies. They have sizes comparable to the Milky Way, but with far fewer stars, distributed sparsely. This is already curious in itself, because it means their luminosity is low and their structure is fragile. The absence of dark matter in this case is even more intriguing, because this matter is precisely what we believe is responsible for keeping galaxies cohesive. Without it, such a light galaxy should have been torn apart by cosmic tidal forces over billions of years. 2 years after DF2's discovery, another similar galaxy was identified, NGC 1052 DF4, and guess what? It also seemed to lack dark matter. The finding reinforced the hypothesis that this wasn't an isolated error, but a real phenomenon. Now there were two examples close to each other, belonging to the same galaxy group associated with NGC 1052, a massive elliptical galaxy that could be involved in their formation and evolution. Some models suggest collisions or close encounters between galaxies can strip dark matter from more fragile systems, leaving behind almost naked galaxies. This idea fits well with the case of DF2 and DF4, since both seem to be gravitationally linked to the giant NGC 1052. It's as if, during past interactions, both had lost their dark matter and survived only with dispersed stars and gases. This type of event, if confirmed, would show that dark matter is even more dynamic than we thought, capable of being redistributed on enormous scales. On the other hand, if we accept the hypothesis that some galaxies don't need dark matter, this also challenges alternative models to this concept's very existence. Theories like MOND, modified Newtonian dynamics, which try to explain galactic movements without resorting to dark matter, assume the discrepancy between visible mass and observed gravity is universal. But DF2 and DF4 don't present this discrepancy. That is, if MOND were correct, they should exhibit the same behavior as other galaxies. The fact they don't reinforces the idea that dark matter actually exists and can be absent in particular cases. This means that, paradoxically, galaxies without dark matter are actually one of the best pieces of evidence that dark matter is real. If it didn't exist, it wouldn't make sense for some galaxies to need it and others not. The simple fact of finding exceptions reinforces the general framework. It's one of those moments when science becomes counterintuitive. Absence is proof of existence. The implications also touch on how we understand universe evolution. If galaxies can lose or never accumulate dark matter, this suggests this material's distribution isn't homogeneous, and initial formation conditions can generate very varied results. This helps explain why the cosmos exhibits such diversity of forms, from well-defined spiral galaxies to almost ghostly structures like diffuse ones. From an observational standpoint, studying these galaxies isn't easy. Since they have few stars, they're extremely faint in the sky. To identify them, powerful telescopes and deep imaging techniques are needed, capturing light that barely reaches us. It was precisely the use of equipment like the Dragonfly telephoto array, an arrangement specialized in capturing objects with low surface brightness, that allowed discovering DF2 and DF4. Another fascinating detail is that these galaxies are almost transparent. In long exposure images, you can see background galaxies through them, as if we were looking through a poorly sewn curtain of stars. This reinforces the impression they're fragile objects, without the gravitational glue of dark matter to keep everything united compactly. The next steps in this investigation involve even more precise measurements of distance and star movement in DF2 and DF4. This is because any small calculation error can significantly alter conclusions. The scientific community remains divided, but with each new observation, it seems clearer that these objects really do challenge the standard. They're not just curiosities, but key pieces for testing the robustness of the cosmological model we use to explain the universe. It's also important to remember that dark matter is still an open concept. We know it exerts gravity, but we don't know what it is. It might be formed by exotic particles not yet detected, like WIMPs or axions, or it might be something totally different that we haven't been able to formulate yet. In this context, every galaxy that doesn't follow the rule becomes an opportunity to refine hypotheses and discard unsustainable models. Cosmologically, DF2 and DF4 allow us to observe star behavior in an environment where dark matter seems absent, providing direct comparison with normal galaxies. This helps calibrate theories and understand to what extent our dependence on dark matter is consistent. And there's still the question of initial formation. Did these galaxies already form pore in dark matter, or did they lose it in violent cosmic encounters? Answering this can give us clues about the processes that shaped the universe in the first billions of years after the Big Bang. If we can trace these systems' dynamic history, we can better understand not just the exceptions, but also the general rule. Meanwhile, the debate remains open. Each new piece of data, whether confirming or refuting dark matter's absence, has enormous weight. Science works in this cycle of hypotheses, observations, and revisions. What seemed impossible, a galaxy without the invisible glue that sustains the cosmos, is now a concrete possibility. And paradoxically, it's precisely this anomaly that might lead us to better understand the essence of what we call dark matter. Magnetar Cosmic Canon. stars that explode in energy bursts capable of destroying planetary atmospheres. Among the most enigmatic objects in the cosmos, magnetars occupy a prominent place. They are extremely rare neutron stars, born after supernova explosions, but distinguished by an almost unbelievable characteristic. They possess the most intense magnetic fields ever identified in the universe. To get an idea, these fields can be up to 1 trillion times stronger than Earth's. From this colossal magnetic force, devastating energy phenomena occur, transforming these stars into true cosmic cannons. The term magnetar was created to designate a specific subcategory of neutron stars. All neutron stars are collapsed remnants of massive stars that exploded as supernovas. But in some cases, the collapse generates a different rotation and an anomalous magnetic configuration, resulting in these extreme objects. They are incredibly small, around 12 miles in diameter, but concentrate more mass than the entire Sun. It's a paradox difficult to conceive, imagining something with a density of billions of tons in each cubic centimeter. A magnetar's main signature is its ability to release violent bursts of radiation, especially X-rays and gamma rays. These eruptions are so intense that, even occurring tens of thousands of light-years from Earth, they've been detected by satellites orbiting our planet. In 2004, for example, an explosion from magnetar SGR 180620 was so powerful it saturated gamma-ray detectors on various space probes. For a few instants, the energy released was greater than all Milky Way stars combined. To understand how this is possible, we need to look inside the magnetar's structure. The gravitational collapse that formed the neutron star compacted its nucleus into an exotic state of matter, where protons and electrons merged into neutrons. In magnetar's case, the magnetic field reaches absurd intensity, deforming even atoms in its interior. This field's pressure is so great, it affects the star's crust itself. When this crust cracks or undergoes readjustments, in a phenomenon called starquake, enormous amounts of magnetic energy are released at once. These bursts often last only fractions of a second, but their intensity is so tremendous they could, theoretically, erase entire atmospheres from nearby planets. The radiation emitted would be sufficient to destroy complex molecules and sterilize worlds that, until then, could be inhabitable orbits. That's why magnetars are seen not just as astrophysical curiosities, but also as potential agents of destruction on interplanetary scales. What draws attention is these objects' rarity. It's estimated that in the Milky Way, there are about 30 magnetars identified to date. This makes them exceptions, almost cosmic anomalies. Most massive stars, when collapsing, give rise to conventional neutron stars or black holes. For a magnetar to emerge, conditions need to be extremely specific, involving initial rotation and magnetic properties of the progenitor star. Unlike black holes, magnetars don't hide their presence behind event horizons. They announce themselves dramatically, with radiation bursts that travel through space and can be observed by specialized instruments. These explosions are usually classified into 3 types: short bursts, intermediate bursts, and giant flares. The first are most common and release less energy. Giant flares, extremely rare, can emit in seconds more energy than the Sun will produce in 100,000 years. The impact these explosions cause on our planet depends only on the distance where they occur. If a magnetar exploded a few hundred light-years from Earth, effects could be catastrophic. Models suggest such an intense gamma-ray burst could affect the ozone layer, allowing harmful solar radiation to directly reach the surface. This would have immediate impact on the biosphere, altering ecosystems, and even causing mass extinctions. Fortunately, no known magnetar is close enough to represent this risk. One of magnetar's most intriguing characteristics is that their magnetic field is unstable. Unlike Earth's magnetic field, which remains relatively constant, theirs undergoes violent rearrangements. These rearrangements not only cause starquakes, but can also deform the star's very structure. There are indications these deformations are capable of emitting gravitational waves, although at intensities very difficult to detect with current technology. Still, the possibility of observing magnetars through these waves opens a new research frontier. In the scientific imagination, magnetars have become almost modern legends. They represent limits of what we know about matter physics in extreme states. Density is such that subatomic particles behave in ways we're still trying to describe. Magnetic force is so tremendous it influences surrounding vacuum, altering photon behavior passing through the region. This phenomenon, called vacuum birefringence, has already been detected in magnetar observations, offering a rare opportunity to test quantum electrodynamics predictions. Despite all their power, magnetars are short-lived objects in astronomical terms. The intense magnetic field, which is their trademark, is also the reason for their instability. In a few thousand years, this field begins dissipating and the star gradually stops presenting violent bursts, becoming a more conventional neutron star. This means that, although rare, magnetars are even more ephemeral, living a brief and explosive phase within cosmic chronology. Each magnetar observation helps adjust our astrophysics models. Satellites like Chandra and XMM Newton have already recorded dozens of bursts, each with unique characteristics. Some seemed accompanied by sudden changes in the star's rotation, called glitches. These events provide clues about how the star's interior responds to extreme pressures, as if we were hearing creaks from a colossal structure adjusting under incomprehensible tensions. There's also a curious aspect. Magnetars might be behind another astronomical mystery, the so-called fast radio bursts, FRBs, extremely brief and intense explosions of radio waves coming from distant universe locations. Although not all FRBs can be explained by magnetars, one was directly associated with one of these objects in 2020, strengthening the hypothesis. This links these exotic stars even more to some of the most mysterious phenomena we've recorded. In the field of scientific speculation, magnetars also raise questions about life's limits in the cosmos. If stellar systems with magnetars in their interior are incapable of maintaining habitable planets due to recurrent explosions, this could affect life distribution in the galaxy. That is, besides study objects, they might be pieces of a larger puzzle about life's rarity or abundance in the universe. A detail that makes these stars even more fascinating is their tiny size. It's counterintuitive to think that something with only 12 miles in diameter can release energy comparable to an entire galaxy's production for brief instants. This disproportion is one of the reasons magnetars are constantly cited as examples of cosmic extremes, small in scale but colossal in effect. Technically, magnetar detection requires observation in X-rays and gamma rays. This makes them invisible to common optical telescopes. Only in energetic wavelengths can we see their explosions, reinforcing the idea that much of the universe is hidden in ranges our eyes don't capture. By following these emissions, we build a kind of medical record for each known magnetar, recording their bursts and behavior changes. Research on magnetars also influences other physics areas. By studying how these magnetic fields deform matter, scientists test theories about superconductivity, particle behavior, and even space-time properties. Each observed burst is a natural experiment, something we couldn't recreate in Earth laboratories, but which the universe provides on a monumental scale. Even being rare and short-lived, magnetars continue appearing in our catalogs, reminding us the Milky Way is a dynamic place. Estimates indicate a magnetar might emerge in our galaxy every 10,000 years, resulting from a particularly favorable supernova explosion. Although this interval is enormous for us, in cosmic scales, it's just a blink of an eye. This means that, at any moment, there might be newly formed magnetars scattered throughout the universe, waiting to be identified. Primordial black holes, hypothetical, formed right after the Big Bang. Among all modern cosmology's ideas, few are as intriguing as the hypothesis of primordial black holes. Unlike the black holes we know formed by massive star collapse, these would have emerged in the first instance after the Big Bang, when the universe was still incredibly dense and chaotic. If they exist, they would be direct witnesses to the cosmos's first seconds and could answer some of current physics' most difficult questions. To understand where this idea comes from, we need to remember that right after the Big Bang, the universe was a hot soup of particles, radiation, and energy. There were no stars, planets, or galaxies, just density fluctuations on a microscopic scale. Some regions were slightly denser than others, and this difference, however minimal, could have led to gravitational collapse on very small scales. In theory, these compressed regions could generate black holes with masses varying from less than an ounce to thousands of times the Sun's mass. This mass diversity is what makes primordial black holes so special. While black holes formed by stars follow a relatively predictable pattern, normally between 3 and a few dozen solar masses, primordials could be much smaller or much larger, depending on local conditions in the young universe. Some models suggest they could be as small as a mountain or even microscopic, but with absurd density. If they really emerged at that time, they would have crossed the entire universe's history until today. And here enters another curious detail. Black holes aren't eternal. According to Stephen Hawking's theory, they emit radiation slowly, losing mass over trillions of years. This evaporation happens faster the smaller the black hole. This means that if extremely tiny primordial black holes exist, many would have already disappeared. But those born with larger masses could still be out there, scattered through space. One reason for such interest is that these objects could explain mysterious dark matter. Today we know about 27% of the universe's content is composed of something invisible that doesn't emit light but exerts gravity. Nobody knows exactly what it is. Some physicists propose that primordial black holes could be natural candidates for this function. They would be invisible in terms of radiation, but could be everywhere, influencing galaxy rotation and cosmic structure formation. This scenario, however, isn't easy to confirm. If primordial black holes were present in large quantities, we should observe certain specific effects. For example, they could distort light from distant stars when passing in front of them, a phenomenon called gravitational microlensing. Searches of this type have been done, like in the Macho project and later surveys, and so far we haven't found sufficient signs to conclude they are dark matter. This doesn't rule them out completely, but greatly limits the space where they can hide. Another possible clue would be in gravitational waves. When two black holes collide, they release waves that spread through spacetime's fabric. Since 2015, with LIGO detection, we know these collisions really happen. Interestingly, some of the first detected events had masses that didn't fit so well in stellar formation models. This led some scientists to speculate, what if these were primordial black holes, created right after the Big Bang, and now meeting billions of years later? Besides dark matter and gravitational waves, there's another aspect where primordial black holes enter the conversation: galaxy origins. One hypothesis is that very massive black holes, formed in the universe's first seconds, could have served as seeds for galaxy formation. Instead of galaxies creating supermassive black holes in their centers, the process would have been the reverse. giant black holes would have attracted matter around them, giving rise to the first cosmic structures. This type of idea helps explain a current enigma: how some supermassive black holes, with billions of solar masses, managed to exist in the first 800 million years after the Big Bang. The time seems too short for them to have grown only from collapsed stars. But if there were already very massive primordial black holes, the equation becomes more plausible. Still, direct evidence remains scarce. Looking for black holes that don't emit light is like trying to find spots of darkness in the dark. But science developed ingenious ways to search for these objects. One is observing cosmic background radiation, the photograph of the universe, at only 380,000 years old. If there were many primordial black holes at that time, they could have left subtle marks in this radiation's distribution. So far, nothing definitive has been found, but new, more precise measurements continue refining possibilities. Another promising field is cosmic rays. Very small black holes, when evaporating via Hawking radiation, could emit high-energy particles detectable here on Earth. We haven't seen clear signs of this yet, but gamma-ray telescopes and particle detectors continue alert, hoping for some indication that many black holes are really evaporating somewhere in the cosmos. The most interesting thing is that even without confirmation, the primordial black hole hypothesis remains relevant because it connects various physics areas. It touches cosmology, explaining universe structure formation, astrophysics, dealing with star and galaxy evolution, and theoretical physics, exploring gravity and quantum concepts. It's one of those themes that, if proven, would reconfigure much of today's science. It's worth remembering that not all models agree on these objects' viability. Some calculations suggest density fluctuations in the primordial universe weren't large enough to form black holes on a large scale. Others point out that cosmic inflation, an accelerated expansion phase right after the Big Bang, could precisely amplify certain regions and facilitate these objects' creation. The discussion is still open, and each new observation helps restrict possible scenarios. Primordial black holes also appear in more exotic contexts. Some theorists suggest they could hide inside planets or stars, altering their internal behavior. Others raise the possibility that if they have very small masses, they might be detected in particle colliders, although this is highly speculative. These ideas show how the concept is fertile and generates hypotheses in various directions. There are also those who relate these objects to mysterious phenomena observed in the cosmos. Fast radio bursts, intense energy emissions of still unknown origin, could be linked to primordial black hole interaction with neutron stars, for example. Although none of this is confirmed, they are investigation lines that keep astronomers attentive. Even without direct proof, the simple possibility already influences our way of thinking. Today, when we look at the sky, we know that besides stars, planets, and galaxies, there might be an invisible population of ancient black holes scattered throughout the universe. If someday we manage to confirm their existence, it would be like opening a safe that holds secrets from creation's first second. Tabby's star, with unpredictable brightness drops that confound astronomers. Among the hundreds of thousands of stars already studied by space telescopes, few have drawn as much attention as the so-called Tabby's star. Officially known as KIC 8462852, it gained its nickname in honor of astronomer Tabitha Boyajian, who led initial analyses of its strange luminosity variations. The story began when the Kepler telescope, dedicated to hunting exoplanets, detected something that seemed to defy all known logic. Unlike other monitored stars, this one presented abrupt and irregular drops in brightness, some reaching 20% reduction. For comparison, when a Jupiter-sized planet passes in front of a star, luminosity drop is only 1%. Something much larger, more complex, and mysterious was happening there. Kepler's method is relatively simple. It observes thousands of stars' brightness and looks for regular drops indicating planet passage in orbit. These drops are predictable and repetitive, making confirmation easy. In Tabby's star case, however, the pattern was chaotic. There was no clear repetition, no stable periodicity. Brightness drops happened irregularly, some fast, others prolonged, as if giant clouds passed before the star without any apparent order. For scientists, this behavior was intriguing from the first moment. One of the initial hypotheses was the presence of a massive field of comets or debris orbiting the star. If a dense fragment cloud passed in front of it, it could cause variable and asymmetric brightness drops. However, the amount of material necessary to justify observations was enormous, raising doubts about the scenario's plausibility. Another considered explanation was the presence of an irregular dust cloud in nearby orbit, but again inconsistencies arose. The brightness drop pattern was too deep to be explained only by common dust grains. The mystery intensified when astronomers noticed the star also showed gradual brightness decrease over decades. Archive images showed that it was becoming less luminous on larger timescales, something completely unexpected. This detail transformed Tabby's star into an even greater enigma. It wasn't just punctual drops, but a long-term dimming trend, as if something were continuously blocking part of its light. In 2015, astronomer Tabitha Boyajian published a paper gathering these observations, and the case quickly became famous, not just among scientists, but also in the general public. The internet nicknamed the star the universe's most mysterious star, and inevitably, some bolder explanations began appearing. Among them, the hypothesis of an alien megastructure, like the so-called Dyson sphere, a theoretical gigantic construction capable of capturing an entire star's energy. Although the scientific community received this idea with skepticism, it helped put the star under media spotlight. Returning to astrophysics' more plausible field, investigations focused on better understanding dust's role. Observations at different wavelengths showed brightness drops were more intense in blue light than red. This detail is important because if a solid object, like a planet, were blocking light, reduction should be equal in all wavelengths. The found difference suggests the material causing drops is semi-transparent and made of very small particles, possibly interstellar dust or circumstellar material. Even so, these clouds' size and density continued being difficult to justify. Would they be remnants of planetary collisions, comet fragments being destroyed when approaching the star, or perhaps dust resulting from still poorly understood stellar activity processes? No hypothesis seemed complete enough to explain all the phenomenon's details. This combination of contradictory clues made Tabby's star a true puzzle for astronomers. In following years, international observation campaigns were organized to monitor the star. The interesting thing is that, unlike many mysteries that end up being solved quickly, Tabby's star continues maintaining its unpredictable character. Each new brightness drop is followed with attention, and each new measurement adds pieces to the enigma. The scientific community still hasn't reached a definitive answer, but has managed to restrict some possibilities. One of the most currently accepted explanations involves irregular dust clouds associated with large orbiting bodies. This material could be constantly produced by fragmentation processes, whether of asteroids or comets. Dust, when dispersing, would create variable light blockages, explaining both rapid and more prolonged drops. Still, the phenomenon's scale continues impressive. To cause up to 20% brightness reduction, these clouds would have to be colossal. Another factor to consider is the star's own nature. KIC 8462852 is an F-type star, slightly hotter and more massive than the Sun. These stars don't usually present the same chaotic luminosity variability we see, for example, in red giants. That is, there's no intrinsic stellar reason explaining such fluctuations. This reinforces the idea that the cause is something external, whether dust or debris. Despite caution, Tabby's star case is a fascinating example of how science deals with the unknown. Instead of quickly dismissing what we don't understand, researchers keep accumulating data, testing hypotheses, and eliminating inconsistent scenarios. It's a slow process, but this is precisely what gives robustness to scientific knowledge. And in this case, the mystery remains alive, which only increases interest in continuing observation. Funding for these observations even came partly through crowdfunding campaigns, supported by the public curious about the possibility of discovering something extraordinary. This shows how Tabby's star surpassed academia limits and gained space in popular culture. It's not common to see thousands of people directly financing astronomical research, but this mystery's appeal was large enough to awaken this engagement. And even if the explanation is just dust, it continues being a remarkable phenomenon. This is because it shows us stellar systems can be much more complex than we imagined. The idea that stars have zones inhabited by dense debris clouds, capable of significantly altering their luminosity, forces us to rethink orbital dynamics and stellar evolution models. Another investigation line suggests part of the dust might originate from the star itself. Stellar mass ejection events, similar but less intense than those seen in giants, could launch material into orbit, creating transitory shadows. Although this type of behavior isn't common in F-type stars, it still can't be totally ruled out. There are also those who consider Tabby's star might have passed through gravitational interactions in its history. If it had distant stellar companions or close passages of other massive bodies, this could have altered its dynamics, disturbing debris disks and generating irregular material flows. This type of scenario is still speculative, but shows how investigation continues open. Whether way, Tabby's star demonstrated something important. Even after centuries studying stars, the universe still reserves surprises. Each normal star we thought we understood can hide peculiar behaviors that challenge our models. In this sense, astronomical exceptions are as valuable as rules, because they force us to expand knowledge's boundaries and consider possibilities we hadn't imagined before. The mystery of this star isn't just a scientific curiosity, but a reminder that the cosmos is more complex and unpredictable than our theories often suggest. Chameleon stars. Astronomy usually works with patterns. Stars of the same type have similar temperatures, colors, and spectra. They evolve relatively predictably, passing through known phases like main sequence, red giant, and white dwarf. But in some rare cases, astronomers have observed stars that seem to break the rules and change appearance suddenly. They're called chameleon stars because they alter their spectrum and even their classification in surprisingly short time intervals. A star spectrum is essentially its fingerprint. When stellar light is decomposed in a prism or analyzed by spectrographs, dark and bright lines appear corresponding to absorption and emission of chemical elements. This pattern allows scientists to identify composition, temperature, and even rotation speed. It's one of modern astrophysics' most reliable methods. That's why when a star changes spectrum, we're not talking about a simple visual detail, but a real and unexpected transformation in its physical behavior. One of the most intriguing examples happened with a star cataloged as a B-type star, and years later reappeared with A-type star characteristics. This would be equivalent to seeing a hot bluish star cool down and become whiter in a matter of decades, something that theoretically should take millions of years. The phenomenon caught scientists by surprise because it contradicted stellar evolution models used until then. Among hypotheses to explain this behavior are abrupt changes in stellar atmosphere. Outer layers of a star can, in certain cases, undergo rapid reorganizations, altering how light crosses these gases. This doesn't mean the entire star changed structure, but that its visible shell behaved unstably. Even so, the effect is strong enough to fool instruments and change its spectral classification. Another possible scenario involves the presence of very intense magnetic fields. In some stars, known as AP or BP stars, magnetism can redistribute chemical elements on the surface. making absorption lines of certain elements disappear or intensify. This creates the impression the star changed identity, when actually we're seeing a temporary superficial reorganization. The presence of stellar companions is also an explanation under study. If a chameleon star is part of a binary system, mass transfer between the stars can rapidly alter their visible properties. Imagine a star sucking material from its partner. Suddenly, its surface composition is altered, new spectral lines appear, and the entire spectrum changes. This type of binary interaction has been seen in other contexts and could justify part of the chameleon behavior. However, there are cases that continue being difficult to fit these explanations. Some stars seem to alternate between spectra almost unpredictably, as if they went through unknown transitional phases. These observations challenge current models and force scientists to consider more complex processes like internal energy oscillations or magnetic cycles not yet understood. The chameleon nickname is quite appropriate because these stars really seem to change color. For the human eye, the difference wouldn't be so perceptible without instruments, but in spectrum graphs, the change is clear. It's like watching a living organism suddenly adapting to a new environment, only on a cosmic scale. The importance of studying these stars goes beyond curiosity. Each deviation from expected behavior is a chance to adjust our stellar evolution models. If stars can change spectrum rapidly, this means there are internal mechanisms much more dynamic than we thought. These discoveries force astrophysicists to recalibrate stellar life chronograms and even rethink traditional classification based on fixed spectra. Another curious point is that chameleon stars aren't abundant. So far, only a few cases have been confirmed, and each was discovered almost by accident in comparisons of data from different epochs. This suggests the phenomenon might be rare or difficult to detect because it requires continuous and long-term monitoring. What we know, therefore, might be just the tip of an unexplored iceberg. Besides scientific impact, these stars also awaken cultural interest. The idea of a star changing appearance in decades inspires parallels with mythological creatures or transformation narratives. But deep down, what really matters is how much they challenge our expectations. They remind us that astronomy, even after centuries of study, still finds unprecedented behaviors in the skies. In practical terms, astronomers use global telescope networks to follow these stars and record their changes. Each new observation is compared to old databases, creating a timeline that helps map transformation rhythm. This work is patient and requires international collaboration, since changes don't follow clear patterns. Some researchers defend that part of chameleon stars might be going through short and rare phases of unstable nuclear fusion. At certain points in stellar life, nucleus reactions can oscillate before stabilizing again. This would generate transitory signals in the atmosphere reflected in the spectrum. If this hypothesis is correct, observing chameleon stars would be like catching a rare stage of a star's life, something that normally would be lost in the vast millions of years of its existence. The study of these objects might also connect to supernova searches. Unstable or rapidly transitioning stars might become candidates for stellar explosions in relatively short timescales. Monitoring their behavior can provide early clues about high-impact cosmic events. Either way, what makes chameleon stars special is unpredictability. Unlike regular phenomena like pulsars or binary eclipses, here we deal with unexpected transformations that challenge traditional categories. This makes each new observation a surprise, and each spectrum an invitation to reconsider what we thought we knew about astrophysics laws. Today, these stars remain as open enigmas. There's no single theory explaining all cases, but rather a set of hypotheses that still need refinement. And while we await new data, they continue reminding us the universe is more dynamic than our models suggest. The night sky might seem immutable, but just look with sensitive instruments to realize even stars can be more inconstant than we ever imagined. Pulsar Lich planets. When we talk about unlikely places to find planets, few examples are as extreme as worlds orbiting a pulsar, and among them, the most famous are those circling pulsar PSR B 1257+12, nicknamed Lich. Discovered in the early 1990s, these planets were the first confirmed exoplanets outside the solar system. What would already be a milestone gained even more prominence because the environment where they were found seemed absolutely hostile, around a dead star emitting radiation in constant bursts. Pulsar Lich is a neutron star. It was born from a supernova explosion when a massive star collapsed and left behind only an ultra-dense core. The result is a celestial body with mass greater than the Sun's, compressed into a sphere only a few dozen miles in diameter. Spinning rapidly, it emits beams of electromagnetic radiation crossing space like lighthouse beams. Whenever this beam crosses our field of vision, we detect a pulse, hence the name pulsar. Discovering planets around such a violent object seemed unlikely, but the detection method worked almost ironically. Pulsars are incredibly regular in their pulse emission, functioning as precise cosmic clocks. Any small perturbation in this rhythm can betray the presence of orbiting bodies. This was exactly what astronomers Alexander Wolskan and Dale Frail noticed in 1992. Subtle variations in pulse arrival time indicated something was pulling the pulsar, causing oscillations in its position. This something was planets. 3 worlds were identified orbiting the pulsar. They received names Draugr, Poltergeist, and Phobator, all inspired by folklore and mythology figures linked to death and the supernatural, in tune with Lich's nickname. Draugr, the smallest, has mass comparable to the Moon's. Poltergeist and Phobator are larger, with sizes close to Earth's. Although orbiting a dead star, they represented the first concrete evidence that planets weren't exclusive to our solar system. The environment, however, is anything but welcoming. Radiation emitted by the pulsar is lethal on any scale, constantly bombarding these worlds with energetic particles. Any atmosphere they had would have been swept away long ago. The surface, if it existed in solid form, would be exposed to radiation levels, making life as we know it impossible to emerge or maintain. These planets are essentially monuments of resistance amid a devastated scenario. This raises the question, how did they get there? One hypothesis is that Lich pulsar planets formed from stellar debris after the supernova explosion. In this scenario, the collapsed star's remains could have organized into a disk of dust and gas, which later condensed into planets. Another possibility is that these worlds already existed before the explosion, but somehow survived the cataclysm. Both explanations are challenging, and astronomers still debate which makes more sense. Whatever the origin, these planets showed something essential. Planetary formation processes are much more varied than we imagined. Until then, the most accepted view was that planets form along with their stars, from the same gas and dust cloud. Lich's system opened a door to the idea that even dead stars can, in certain circumstances, harbor orbiting worlds. This significantly expands the spectrum of places where exoplanets can exist. The fact they were the first confirmed exoplanets also has curious symbolism. The first official discovery didn't come from a normal star similar to the Sun, but from a radically different, unlikely, and hostile environment. It's as if the universe chose an extreme example to announce, planets are everywhere, even where you least expect them. Over time, studies of these worlds helped improve pulsar detection techniques. The timing method, Precisely analyzing pulse intervals continues being one of the most reliable when dealing with neutron stars, although it hasn't proven as effective for detecting large exoplanet populations. It was fundamental in consolidating the idea that planets exist abundantly outside our system. Lich planets also raised speculations about what their surfaces would be like. Although we can't observe them directly, models suggest they would be rocky bodies, perhaps with different compositions from what we know. The absence of atmosphere would mean exposed surfaces, continuously bombarded by radiation. If you could stand on one of them, which isn't possible of course, you would weigh instantly hundreds of thousands of times more than here. The sky would be dominated by regular flashes from the pulsar, like a cosmic strobe light, marking time implacably. Even in such extreme environments, some scientists consider alternative habitability scenarios. It's unlikely life would flourish on the surface, but theoretically it could exist below it, protected by thick rock layers. Radiation would penetrate only to a certain point, and underground life forms, perhaps similar to microorganisms surviving in extreme conditions on Earth, could resist. This is speculation, of course, but illustrates how astrobiology expands to consider even the most unlikely scenarios. Lich pulsar system also reinforces the importance of archive astronomy. It was by revisiting data collected by Kepler and ground observatories that scientists noticed additional details about brightness drops and variations associated with these worlds. This old data still today helps refine mass, orbit, and system stability calculations. Beyond science, Lich pulsar planets became cultural icons among astronomy enthusiasts. Their association with supernatural entity names and the fact they're around a living dead star reinforced the find's enigmatic character. It's a reminder that even in places where stellar death seemed definitive, there can still be remnants of complexity, like planets persisting amid chaos. Today, we know planets around pulsars are rare. Very few examples have been detected beyond Lich system. This suggests that, although possible, this type of configuration isn't common in the universe. But the fact it exists was enough to shake paradigms and open new research fronts. The future of these planets is predictable in general terms. They'll continue orbiting their dead star until the pulsar itself fades completely. This will take billions of years, much longer than the universe's current age. That is, we're still seeing these objects in an intermediate phase of their long trajectory. Meanwhile, they continue serving as a landmark for our studies and as an example of how relatively common stars can have such extreme destinies. Lich pulsar planets, therefore, aren't just a footnote beside one of the most famous neutron stars. They're some of the most important objects ever discovered for exoplanet astronomy. Their discovery in such an unlikely environment proved planets can form or survive in conditions we never imagined. And at the same time, they're a reminder that the universe is more creative and resilient than our models often suggest. Vampire and zombie star. In astronomy, some popular names seem straight out of a horror book. This is the case with so-called vampire and zombie stars. The nickname isn't an exaggeration. In very close binary systems, one star can literally suck matter from its companion, growing at the other's expense. In some cases, this unequal relationship awakens a star that was practically dead, making it shine again unexpectedly. It's a dramatic cosmic dance, as violent as it is fascinating. To understand this phenomenon, we need to remember many stars don't live alone. Actually, most of them are born in pairs or even groups. In binary systems, two stars orbit a common center of mass, as if they were partners trapped in an eternal dance. When they're very close, this relationship can become intense. If one of the stars grows and expands toward the red giant phase, its outer atmosphere can extend so much that part of the material begins escaping and falling onto the companion. This is where the story gains a vampiresque tone. What happens in this process is called mass transfer. The denser star, usually a white dwarf, begins accumulating material stripped from the companion in an accretion disk. This disk spins at high speed, heated to immense temperatures by friction, releasing radiation in large quantities. This intense brightness is one of the signs astronomers observe when looking for this type of system. In some cases, the star-donating material gets increasingly exhausted until it loses much of its mass while the predator grows or becomes more active. The zombie star metaphor arises in another scenario. Imagine a white dwarf, which is basically the dead core of a star that already shone in the past. Normally, this type of object just cools slowly without major events. But if it's part of a binary system and begins pulling matter from its companion, this extra mass can reignite temporary nuclear fusions on its surface. What was practically extinguished returns to emit energy violently, as if the star had resurrected. Hence, the zombie star nickname. These systems aren't just curiosities, they play an important role in some of the universe's most explosive events. A white dwarf accumulating too much matter can surpass the so-called Chandrasekhar limit, about 1.4 times the Sun's mass. When this happens, it can no longer sustain itself by electron quantum pressure and explodes as a Type Ia supernova. These supernovas are so luminous they can be seen in distant galaxies and, more importantly, function as standard candles in cosmology, helping scientists measure universe distances and even confirm dark energy's existence. Another possible outcome is even more dramatic. Instead of exploding as a supernova, the white dwarf might undergo instabilities that transform it into a neutron star or direct collapse. Each case depends on masses involved, mass transfer rate, and orbital characteristics. This diversity of outcomes makes vampire and zombie star binary systems a very rich research area. From an observational standpoint, astronomers can identify these pairs in various ways. One is precisely the light emitted by the accretion disk, which can vary rapidly, producing characteristic light curves. Another is the presence of intense X-ray emissions, since material falling onto the white dwarf or neutron star heats to millions of degrees. These signals allow locating systems thousands of light-years away, even amid galaxies' luminous background. The dramatic behavior of these stars also gives rise to phenomena known as novae. When the white dwarf accumulates a certain amount of hydrogen on its surface, this material can undergo sudden nuclear ignition, producing a relatively small explosion compared to a supernova, but still extremely bright. The star seems to light up from nowhere, surprising observers. The term nova comes precisely from this effect. In the past, astronomers thought a new star had appeared in the sky. Today, we know this was actually a vampire system reigniting for a brief instant. And if we think long-term, these relationships can completely change both stars' destiny. The donor, by losing mass, might end up reduced to a degenerate core, practically extinguished. The receiver, in turn, might transform into something much more massive or even provoke explosions capable of illuminating entire galaxies. It's as if these systems were small cosmic extreme factories, responsible for some of the most spectacular events we can observe. The vampire nickname isn't just a fun metaphor, but also an effective way to communicate to the public what happens there. After all, the image of a star sucking another's life clearly translates the process's essence. Similarly, the idea of a resurrected zombie star helps illustrate some dead star's capacity to shine again when receiving fresh matter. It's science, but with an imagination touch, making everything easier to visualize. The most curious thing is that, despite the drama, these systems aren't as rare as imagined. It's estimated that much of our galaxy stars were born in binary or multiple systems. Many are destined, sooner or later, to pass through mass transfer episodes. This means vampire and zombie stars might be scattered throughout the Milky Way, even if only a fraction is clearly identified. The study of these phenomena also has practical implications. As mentioned, Type 1a supernovas, often originating from these systems, are fundamental tools for cosmology. It was precisely by observing this type of explosion that astronomers discovered, in the 1990s, that universe expansion is accelerating. In other words, systems beginning with one star sucking another can, in the end, help us understand the entire cosmos's destiny. In physics terms, they also challenge our models. Mass transfer dynamics is extremely complex. Small variations in rotation speed, magnetic field, or orbital alignment can completely change the system's behavior. Supercomputer simulations try reproducing these scenarios, but reality is usually more chaotic than models can predict. Each new observed system brings surprises. And of course, there's the aesthetic side of the phenomenon. If we could observe closely a star pair in this process, we would see a constant flow of material being stripped from one and forming a bright whirlpool around the other. This visual spectacle, invisible to naked eye but revealed by X-ray and ultraviolet telescopes, is a reminder that cosmos violence can also be incredibly beautiful. In some extreme cases, mass transfer can lead to complete stellar mergers. Two white dwarfs, for example, can get so close they end up uniting into a single body. Depending on total mass, this can result in an explosion or a new, more massive star. These mergers are candidates for explaining high-energy phenomena still intriguing astronomers, like certain types of rapid explosions detected in distant galaxies. The zombie nickname also fits well when we think of recurrent novae, stars that go through repeated explosion and extinction cycles. It's as if they refuse to die completely, coming back to life from time to time thanks to matter stolen from the companion. This cyclical behavior has been documented in various systems, and each explosion provides valuable data about nuclear physics under extreme conditions. Even with so many advances, there are still open questions. How exactly does mass transfer initiate in different binary types? What are the limits defining whether the system will end in a nova, supernova, or merger? And how many of these events actually happen in the Milky Way each century? These are questions motivating astronomers to continue monitoring the sky for clues. These systems remind us that even the most dramatic cosmic events can have surprisingly long developments. A vampire star might spend millions of years slowly draining its companion before the final explosion. It's a patience that contrasts with the violence of the final outcome, showing how the universe operates on timescales very different from human experience. Looking to the future, new space telescopes and monitoring missions promise to discover many more examples of these systems. Each new vampire or zombie star identified adds pieces to the cosmic evolution puzzle, helping us understand not just individual stellar destinies, but how matter and energy recycle throughout the universe. The universe's fastest pulsar, PSR J1748-2446ad, a neutron star spinning 700 times per second. When talking about stars, most people think of something fixed, shining quietly in the sky. But not all are like that. Some stars, after living intense and violent lives, end up transformed into compact objects spinning at absurd speeds. This is the case with pulsars, remains of massive stars that collapsed after supernova explosions. They're already extreme by nature, but there's one pulsar in particular that surpasses all others. PSR J1748-2446ad, the fastest pulsar found in the known universe. This object is about 18,000 light-years away, in globular cluster Tarzan 5, a dense Milky Way region full of old stars. It was discovered in 2005 when radio telescopes detected its characteristic signature, regular radiation beams, as if it were a cosmic lighthouse blinking at very short intervals. The impressive detail is this rotation's frequency. PSR J1748-2446ad spins an incredible 716 times per second. This means that, in less than an eye blink, it has already completed hundreds of turns around itself. To visualize, imagine Earth, which takes 24 hours to spin once. Now think of an object about 12 miles in diameter, smaller than an average city, spinning 716 times each second. The speed on the pulsar's surface is so high it approaches a quarter of light speed. It's something we simply have no parallel for in any other known natural environment. But how can something like this exist without falling apart? The answer lies in a neutron star's absurd gravity. After a massive star explodes as a supernova, the core that survives collapses under its own weight. Protons and electrons merge, forming neutrons compacted in a dense and exotic matter state. The result is an object with mass greater than the Sun's compressed into a radius of just a few miles. Gravity is so intense it keeps the entire star cohesive, even with furious rotation. This balance, however, has limits. Theoretically, there's a maximum speed for pulsar rotation. If it spins too fast, centrifugal force overcomes gravity and begins tearing matter from the surface. PSR J1748-2446ad is dangerously close to this limit. Some models suggest that if it passed 1,000 rotations per second, it would probably disintegrate. It is therefore a living sample of the extreme point where physics can still hold an object together. Another fascinating detail is how these pulsars reach such speeds. Many aren't born spinning so fast. Instead, they go through a process called recycling when they have a nearby stellar companion. Matter from the companion falls onto the pulsar in an accretion disk, transferring angular momentum. It's like pushing a carousel. Each particle of matter that falls makes it spin faster. PSR J1748-2446ad probably went through this phase at some point, accelerating until becoming the cosmic champion we know today. Pulsars are also famous for the radiation beams they emit. Since they have intensely strong magnetic fields, rotation makes charged particles accelerate and emit radiation toward space. If these beams are aligned with Earth, we detect them as regular signals at intervals corresponding to the star's rotation. In PSR J1748-2446ad's case, this cadence is so fast that signals repeat hundreds of times per second, transforming it into a kind of perfect metronome of the universe. These signals aren't just curiosities. Pulsars are used as precise tools to study the cosmos. Some function as clocks more stable than any instrument built by humans. In the case of the fastest pulsar, its study helps refine PSR, ultra-dense matter physics limits. The way it maintains stability gives clues about how neutrons behave in states we can't reproduce in laboratories. The most impressive thing is that even so far away, we can measure these details with extremely high precision. Radio telescopes capture pulses' regularity, and small variations can indicate companions orbiting or even subtle gravitational waves passing through space. Pulsars like this are true natural observatories, providing information about the universe regions that otherwise would remain inaccessible. The discovery of PSR J1748-2446ad also raised an interesting question. Might there be even faster pulsars? Theory allows rotations up to 1,200 times per second before the star breaks apart. This means that somewhere there might be an even more extreme object that has escaped our observations so far. Finding it would be like discovering stellar physics, the definitive limit. Meanwhile, the current champion continues fascinating. Knowing that an object only 12 miles in diameter can spin so fast and remain stable is a reminder of how nature's laws behave, counterintuitively. In our daily lives, nothing comes close to such conditions. It's like comparing a bicycle to a particle collider. Both spin, but on scales so different, they seem like distinct worlds. And there's also the energy question. The pulsar's absurd rotation carries a gigantic amount of kinetic energy. Part of this energy is released as electromagnetic radiation, but the object still manages to stay spinning for billions of years, slowly decelerating. Even so, each second it emits signals that travel through space and that we, 18,000 light-years away, can capture with remarkable precision. PSR J1748-2446ad's position within a globular cluster is also relevant. Tarzan 5 is a region where stars are very close, increasing chances of gravitational interactions and compact binary system formation. This environment probably favored the recycling process that accelerated the pulsar. It's not just an isolated object, but part of a busy cosmic neighborhood that helps shape its history. Another curiosity is that despite spinning so fast, the pulsar shows no signs of being about to break apart. This suggests matter inside a neutron star is even more resistant than the most conservative models predicted. Perhaps there are exotic phases of nuclear matter, like the so-called quark matter, that allow this stability. If so, each rotation of PSR J1748-2446ad is a clue that the universe hides matter forms not yet fully understood. From a practical standpoint, studying this pulsar also helps improve our understanding of gravitational waves. If it has small deformations in its shape, its rotation might emit subtle ripples in spacetime. Detecting this type of signal would be another gigantic advance for physics, and objects like this are ideal candidates for this research. Some call PSR J1748-2446ad the metronome star, for the impressively constant rhythm of its pulses. And indeed, this regularity makes it almost hypnotic for astronomers who study it. Each pulse is like a cosmic beat, reminding us that the universe, however chaotic it seems, also has incredibly precise rhythms in its depths. It's worth noting that observing this pulsar in detail is not easy. It's not among the brightest, and its position in Tarzan 5, a region full of stars and interstellar dust, complicates measurements. Even so, advances in radio telescopes and signal processing techniques manage to identify its speed with confidence. This is another example of how modern technology manages to transform weak signals into revolutionary discoveries. However extreme it is, PSR J1748-2446ad also helps us remember something important. Neutron stars are natural destinations for many massive stars. Although its rotation is uncommon, the process that formed it isn't. This means that scattered throughout the universe, there must be millions of pulsars, each with its own stories and particularities. Studying the fastest of them is in a way studying all the others' limits. Hypervelocity stars. When we think of stars, the image that comes to mind is usually something stable, fixed in the sky. Since childhood, we learn to identify constellations that seem immobile, faithful to their position night after night. But this sensation is illusory. All stars are in motion, orbiting the galaxy's center in smooth and relatively orderly trajectories. Some, however, completely escape this pattern. They're called hypervelocity stars, true cosmic projectiles shot at speeds that defy imagination. The first time astronomers encountered this type of star was in the early 2000s. When analyzing sky surveys, searching for objects with unusual velocities, researchers found stars traveling so fast they couldn't simply be orbiting the Milky Way. Some were literally on escape routes, capable of fleeing the entire galaxy's gravity. The discovery was shocking, because until then it was believed only small particles or gas clouds could achieve this feat, never entire stars with masses similar to the Sun's. The most famous case is star US 708. Located about 26,000 light-years away, it was identified as a hot subdwarf, traveling at approximately 745 miles per second. This equals more than 2.6 million miles per hour, fast enough to go from Earth to the Moon in just 5 minutes. To put in perspective, the Sun takes about 220 million years to complete one orbit around the galaxy's center. US 708 is crossing the Milky Way with enough energy to never return. The inevitable question is, how can an entire star be accelerated to such absurd speeds? The most accepted explanation involves interactions with supermassive black holes. At the Milky Way's heart exists Sagittarius A, a black hole with millions of times the Sun's mass. If a binary star system approaches this region too closely, the intense gravitational field can literally tear one of them away and hurl it outward at extremely high speed, while the other falls toward the black hole. It's a violent mechanism, but extremely efficient at transforming stable systems into true cosmic bullets. In US 708's case, the scenario might have been even more dramatic. Evidence suggests it was originally part of a binary system where a stellar companion exploded as a supernova. When this happened, the explosion broke gravitational balance and launched US 708 on a free trajectory, accelerated even more by the shock wave. It's as if a bomb had exploded next to it, giving it a colossal push. This type of event is rare, but explains why US 708 doesn't seem to have come directly from the galaxy's center, but from a more distant region. This detail shows hypervelocity stars don't have a single origin. Some are probably the result of direct interaction with the Milky Way's central black hole, while others are hurled by stellar explosions in binary systems. In all cases, the result is the same: stars traveling at speeds so high that they challenge the very idea of belonging to a galaxy. The destiny of these stars is equally fascinating. Once they reach the so-called escape velocity, they have no way to be pulled back by the Milky Way's gravity. This means they will eventually wander through intergalactic space, crossing the void between galaxies. Imagine a solitary star, with its planets, if any survive, traveling for billions of years without ever returning to a stellar community. It's a journey without return, condemned to eternal exile. From a scientific standpoint, studying hypervelocity stars is a unique opportunity. These stars' trajectory and velocity serve as clues about Milky Way dynamics and the central black hole's role. They're like cosmic messages, carrying information about violent events we can't observe directly. By tracing their origins, astronomers can reconstruct close encounters between stars and black holes, or even supernova explosions in binary systems. There's also practical utility. Hypervelocity stars help map the galaxy's invisible mass. As they cross the Milky Way, their trajectory is influenced by dark matter distribution. By comparing expected route with observed route, it's possible to infer the quantity and location of this mysterious substance composing much of the universe. In this sense, each hypervelocity star is a natural probe, traveling through regions we could hardly explore otherwise. Another curious detail is the idea of stars traveling at millions of miles per hour isn't just theoretical whim. There are entire catalogs with dozens of confirmed candidates, and new ones continue being discovered with modern telescopes. The European Space Agency's Gaia mission, which precisely maps billions of stars' movements, has been especially useful for identifying these cosmic fugitives. With each new analysis, more examples appear, suggesting the phenomenon might be more common than we imagined. And this leads to an interesting question. Could hypervelocity stars carry planets with them? If a star with planetary systems were hurled out of the galaxy, some of its worlds could continue orbiting normally, just in a new scenario, without the Milky Way's protection. They would be galactic orphan planets, traveling with their star through intergalactic void. Although there's no observational confirmation yet, the possibility is real and adds an almost poetic level to the idea of entire worlds condemned to cross dark space forever. The study of these stars also sheds light on risks of close encounters with the central black hole. Of course, Earth is safe. We're 26,000 light-years from Sagittarius A*, but stars born in closer regions run the risk of being ejected. This means the black hole isn't just a devourer, but also a launcher of cosmic projectiles. The violence of these encounters helps explain part of the chaotic dynamics shaping the galaxy's heart. Another intriguing aspect is these stars' lifespan. Many are relatively young, indicating they were ejected shortly after formation. This suggests regions near the supermassive black hole might be more active and productive in terms of stellar birth than thought. Studying these traveling stars, therefore, also helps us understand star formation and evolution in extreme environments. US 708 in particular continues being one of the fastest stars ever recorded. Each second it moves away from the Milky Way at a speed defying any comparison with objects from our daily lives. To get an idea, if we tried replicating this velocity with a spacecraft, we'd need billions of years of technological advances. It's a reminder that nature has mechanisms much more powerful than anything we can imagine building for now. In the future, more advanced telescopes will be able to reveal even more examples and details about these stars. There are already proposals to use instruments capable of detecting specific chemical signatures, identifying if they were affected by supernova explosions or interactions with black holes. The more we learn about them, the more we realize they're not just astronomical curiosities, but fundamental pieces for assembling the galactic dynamics puzzle. And there's also the question of long-term consequences. When these stars eventually reach intergalactic space, they might encounter other galaxies' gravitational fields, or even be captured by other stellar systems. It's a reminder that, on cosmic scales, nothing is permanent, and even the most stable structures are subject to change over time. Hypervelocity stars, therefore, represent more than exceptions to the rule. They're witnesses to the universe's dynamic nature. Examples of how gravitational forces can reshape entire systems in relatively short periods. And while they travel toward their galactic exile, they carry with them information about some of the most violent and energetic processes known to astronomy. The fact we can observe and study these stellar fugitives is also testament to how far our observational capabilities have advanced. Detecting a star moving at millions of miles per hour, determining its trajectory and origin, and reconstructing the violent event that launched it, all this was unthinkable just decades ago. Today, it's routine science, albeit science dealing with some of the most extraordinary phenomena in the cosmos. Binary black holes in merger, colossi that collide and release gravitational waves. When we talk about extreme phenomena in the universe, it's hard not to think of black holes. They're already impressive alone, with gravity so intense that not even light can escape. But things get even more dramatic when we're not talking about just one, but two black holes orbiting each other. These pairs, called binary black hole systems, are scenarios where physics reaches its limit. And when they finally collide, the result is one of the most powerful events ever observed in the cosmos: black hole merger. For a long time, the idea of observing this type of collision seemed impossible. Black holes, after all, don't emit light. They're invisible by definition. But in 2015, a century after Albert Einstein predicted gravitational waves' existence, the LIGO collaboration first detected the echo of a black hole merger. It was a historic moment. For the first time, we weren't just seeing the universe with telescopes, but literally hearing space-time vibrate with the impact of two cosmic colossi. To understand this grandeur, we need to imagine the scene. Two black holes, each with dozens of the sun's mass, spin around each other at increasing speeds. With each orbit, they emit gravitational waves, subtle distortions in space-time's fabric that spread like ripples in a pond. These waves carry away energy, making the black holes approach each other more and more. The process can last millions or billions of years, until, in the final instant, they collide in a fraction of a second. The collision releases more energy than all the stars in the universe were emitting at that moment combined. But almost all this energy comes out as gravitational waves, not light. That's why common telescopes can't capture this spectacle. Only specialized detectors, like LIGO's enormous interferometers in the United States or Virgo in Italy, are capable of perceiving the minuscule distortions these waves cause when passing through Earth. We're talking about distance variations smaller than a proton's diameter, measured in 2.5-mile-long arms. The most incredible thing is that we can detect this. The first confirmed event, called GW150914, involved the merger of two black holes with masses of 29 and 36 times the Sun's. The result was a single black hole of 62 solar masses. The difference of 3 suns between the initial total and the final didn't disappear. It was converted entirely into gravitational waves. In energy terms, it's as if 3 entire suns were destroyed in an eye blink, but transformed not into light or heat, but into pure space vibration. Since then, dozens of other similar events have been recorded. Some involve relatively small black holes, others present colossal masses reaching hundreds of suns. Each detection adds pieces to a larger puzzle: how these binary systems form, in what regions of the universe they arise, and how many exist. This has helped scientists better understand not just black holes, but also massive star evolution that gives rise to them. One central question is, where do these pairs come from? There are 2 main hypotheses. The first is that they're born together, like 2 massive stars that explode as supernovas almost simultaneously and leave behind 2 black holes gravitationally bound. The second is that they form more chaotically, in dense stellar clusters, where close encounters eventually join 2 black holes that previously weren't companions. Observations of their masses and orbits can help distinguish between these scenarios. Another fascinating aspect is what happens at the merger moment. Supercomputer simulations show that as black holes approach, space around them distorts in almost unimaginable ways. If we could observe closely, we'd see time stretch and contract, particle trajectories curve in strange spirals, and gravitational energy pour through the universe like a silent roar. At the collision instant, a larger black hole forms, which goes through a brief oscillation period before stabilizing its shape. These sound signals from mergers are actually what detectors record. Each event generates a characteristic pattern, nicknamed chirp, a rapid increase in gravitational wave frequency and intensity as black holes approach and collide. It's almost like hearing a musical note rise in pitch and suddenly end. For scientists, each chirp is a unique signature revealing masses, distances, and even details about involved black holes' rotation. With these detections, we enter a new era of astronomy, gravitational astronomy. Before, our knowledge came mainly from light, optical, radio, X-ray telescopes. Now we have access to a completely different form of information capable of crossing dust, gas, and any barrier that would block electromagnetic radiation. Gravitational waves reach us almost untouched from their origin, bringing a pure portrait of the cosmos' most violent events. And it doesn't stop there. One great expectation is observing mergers involving not just black holes, but also neutron stars. These events, besides emitting gravitational waves, can produce light, gamma rays, and other signals conventional telescopes can detect. We were already lucky to observe one such case in 2017 with two neutron star merger, but binary black holes continue being masters of silence. We can only hear them, never see them directly. These discoveries' scientific importance is immense. Knowing how many binary black holes exist helps better understand massive star formation in the primitive universe. Additionally, measuring gravitational wave strength and frequency allows us to directly test general relativity theory in extreme regimes. So far, all observations confirm Einstein's predictions with impressive precision. Another point is that these mergers function as cosmic lighthouses. Gravitational waves carry information about the distance where the event occurred. Crossing this data with galaxy observations in the same region, astronomers can refine measurements of the universe's expansion rate. In other words, black hole collisions can help us measure the cosmos itself on gigantic scales. And there's still the diversity question. Some detected mergers involved black holes with unexpected masses, outside ranges predicted by stellar evolution models. This suggests we still don't fully understand how these objects form. Perhaps some black holes originated from previous mergers, accumulating mass in a cascade process. Or perhaps there are stellar pathways not yet described. In the future, new observatories will expand this window even further. The LISA project, planned by ESA and NASA, will be a space gravitational wave detector with million-mile-long arms. It will be capable of detecting mergers involving supermassive black holes, much larger than those we observed so far. These events should release even more absurd amounts of energy, echoing across billions of light-years. Thinking about two black holes colliding might sound abstract, but ultimately, it's a story about how the universe recycles matter and energy on gigantic scales. Stars are born, live, and die, leaving black holes as inheritance. These holes, in turn, dance around each other until merging, creating even more massive objects. It's a cycle of destruction and creation that ultimately shapes galaxy structure and influences cosmic evolution. If today we can hear this process, it's because human technology reached a remarkable point. Detecting gravitational waves is like perceiving the sound of a pin dropping amid a storm, and yet we manage. Each new detection is a reminder that even facing unimaginable forces, we can decipher the subtle signals the universe sends us. Binary black holes in merger are therefore more than cosmic curiosities. They're natural laboratories, allowing us to study physics under conditions impossible to reproduce here on Earth. They represent the union of theory, observation, and technology in one of modern science's most impressive achievements. And at the same time, they're a grandiose spectacle constantly happening somewhere in the universe, while we, small observers, learn to listen to their echoes. The so-called forbidden stars. Stellar physics is one of astronomy's most well-established fields. We have models capable of predicting how stars are born, evolve, and die based on parameters like mass, chemical composition, and age. This confidence is the fruit of decades of observations and repeatedly tested theories. But as in all science areas, sometimes exceptions appear that seem to mock these rules. This is where the so-called forbidden stars enter, objects exhibiting properties that shouldn't be possible according to what we know about stellar stability. The forbidden nickname comes precisely from the fact they seem to violate laws describing stellar balance. This balance, known as hydrostatic equilibrium, is simple in theory. Gravity tries collapsing the star inward, while radiation pressure produced by nuclear fusion pushes it outward. When these two factors compensate, the star remains stable. But forbidden stars seem to escape this logic. Some are hotter than they should be. Others seem to have luminosities incompatible with their mass, and there are cases where chemical composition doesn't fit what models predict. A classic example is the so-called supermassive blue stars that remain stable longer than theory allows. Very large stars should burn their fuel so rapidly they couldn't sustain themselves for millions of years in the form we observe them. However, some of these stars exist in both young and old stellar populations, suggesting something in their internal structure is more efficient than we thought. This raises doubts about how convection and rotation influence energy distribution in their interior. Another curious case involves stars known as unstable yellow supergiants. They should oscillate violently in brightness or collapse rapidly, but some seem to maintain stability on timescales that don't match calculations. These examples indicate the stellar life cycle might be more flexible than textbooks suggest, and that factors like magnetic fields or differential rotations might play still underestimated roles. One of the most intriguing candidates for the Forbidden Star title is a group of objects called hot hybrid subdwarfs. They emit radiation at levels far above expected for their mass and composition. Part of the mystery lies in them presenting helium-rich atmospheres, but without hydrogen traces that should be present in greater quantity. The fusion process in their cores doesn't easily fit what we know, and there's still no total consensus on how they manage to remain stable without collapsing or exploding. Additionally, there are also stars with magnetic fields so intense they defy conventional physics. Some giant magnetic stars, known as AP and BP stars, exhibit strange surface chemical compositions with unusual abundance of elements like silicon, chromium, and strontium. The most accepted explanation is that colossal magnetic fields reorganize plasma on their surface, but even so, details about how these fields arise and maintain over millions of years remain unclear. The study of these forbidden stars isn't more than curiosity. They function as natural laboratories, testing theory limits. When a model can't completely explain what we see, this doesn't mean it's wrong, but that it needs refinement. On several occasions, it was precisely these anomalies that led to significant advances in astrophysics. For example, the first observations of anomalous stellar pulsations opened the way to astroseismology, a technique that today allows us to study star interiors with unprecedented precision. The forbidden nickname may sound like something definitive, but actually it's temporary. None of these stars really violates physics laws. What happens is our equations still don't capture all the details of their structure and evolution. Think of them as puzzles, pointing to parts of theory where there's still room for adjustments. It's as if the universe were showing us, almost provocatively, that there will always be exceptions to keep us alert. A famous example was the cold supermassive stars. Observations showed some giant stars seemed cooler than they should, considering their size and brightness. For a long time, this didn't make sense within standard models, but new simulations, including rapid rotation and internal element mixing roles, managed to bring calculations closer to observations. In this case, forbidden stars didn't break any law, just revealed our model was too simplified. Another case is the so-called hyper-metal poor stars with extremely low metal content. According to theories, such stars shouldn't exist nowadays because they would be born unstable and rapidly collapse. But some have been found in the Milky Way, dating billions of years ago. The explanation is still debated. Perhaps they formed under extremely rare conditions, or perhaps we underestimated low-mass stars' ability to survive even with few heavy elements. Forbidden stars also play an important role in testing our understanding of nucleosynthesis, the element formation process inside stars. Some present chemical element proportions that don't match what nuclear models predict. This might indicate there are additional mixing or mass loss processes happening unexpectedly. Solving these enigmas is essential for understanding how elements composing planets and eventually life were produced. With each new telescope generation, more candidates for this category arise. With current instruments, we can measure brightness and spectral variations with previously unthinkable precision. This means our strange stars list tends only to grow. The challenge is separating what's really a new phenomenon from what's just misinterpretation of data. Often, so-called forbidden stars end up finding explanations within known models, but which needed refinement. And this is where science's beauty lies. These objects are reminders that the universe is always more creative than our formulas. Forbidden stars force us to review concepts we considered consolidated, and this opens paths for discoveries going far beyond themselves. When trying to explain why a star seems impossible, we end up understanding better how all others work. From an observational standpoint, many of these stars are still difficult to study because they're distant or because companion brightness interferes with measurements. But space missions like the TESS telescope and James Webb promise to bring increasingly detailed data. With them, we'll be able to investigate not just luminosities and temperatures, but also atmospheric composition and even internal dynamics through astroseismology. Some astronomers even joke that forbidden stars are like the universe's rebels. They refuse to follow simple rules we apply to their more well-behaved sisters. But deep down, it's these rebellions that enrich science. Each strange star is a reminder that the cosmos wasn't made to fit overly elegant models. In pedagogical terms, these stars also have a special role. They're ideal examples for teaching how science deals with anomalies. Instead of dismissing or ignoring what doesn't fit, scientists investigate, accumulate evidence, and reformulate hypotheses. What was forbidden at one moment can become perfectly understandable the next when we have more data and better theories. It's likely that in coming decades, many stars today considered forbidden will cease to be a mystery. New computational simulations, combined with more detailed observations, should clarify how they manage to maintain stability under apparently impossible conditions. Some will become resolved cases. Others, however, will certainly emerge to take their place. After all, the more we look at the universe, the more exceptions we discover. The important thing is that forbidden stars remind us that science is a continuous process of discovery and revision. What seems impossible today might be commonplace tomorrow, and that's precisely what makes astronomy so fascinating, the constant possibility that the next observation will challenge everything we thought we knew. Quark stars. When talking about extreme objects in the universe, we usually think of black holes. They represent gravity's end point, where nothing escapes. But there's an intermediate category, less known, that might be as impressive: the so-called quark stars. They're hypothetical, meaning we're still not sure they really exist. But if they do, they might be even denser and stranger than the famous neutron stars. To understand where this idea comes from, we need to start with neutron stars. Imagine a star with mass several times greater than the Sun's. When it reaches life's end, it explodes as a supernova and leaves behind an extremely compact core. This core, crushed by gravity, is formed almost entirely by neutrons, particles that, along with protons, compose atoms. A neutron star concentrates more than the Sun's mass in a diameter of only about 12 miles. It's such absurd density that a teaspoon of this matter would weigh billions of tons on Earth. Now imagine gravity pressure was even greater, so great that neutrons themselves couldn't maintain themselves as they are. Instead, they would be broken into their most fundamental components, quarks. Quarks are elementary particles forming protons and neutrons. If a star reached this point, we'd have a quark star, an even more compact sphere, formed by a sea of free quarks, perhaps mixed with gluons, particles maintaining nuclear cohesion. This is the theory's basis. When density surpasses the limit supported by neutrons, they melt into quarks. The result would be a type of matter different from everything we know, called quark matter or quark-gluon plasma. This same substance has been studied in particle accelerators here on Earth, like the Large Hadron Collider, LHC, but only under microscopic conditions and for tiny instants. In a quark star, it would exist on astronomical scale. Such a star's size and density would be impressive. It would have practically the same mass as a neutron star, but be even smaller in diameter, perhaps only 6 or 7 miles. The more compact, the greater surface gravity. Density would be so colossal that a grain of quark matter sand could weigh more than Mount Everest. It's difficult even to put into words how extreme this matter form would be. But do they really exist? This is the big question. Astronomers have already detected compact objects with masses and sizes that don't fit well in traditional neutron star models. Some of these cases raise the hypothesis that perhaps we're observing quark stars without realizing. The problem is distinguishing a neutron star from a quark star at distance is an enormous challenge. Both are small, dense, and don't emit their own light, only residual radiation and indirect effects of their gravity. One possible clue would be in their cooling. Neutron stars release heat slowly, but a quark star could have different mechanisms, perhaps cooling faster due to interactions between fundamental particles. If we observe an object cooling at an unexpected rate, this could be evidence we're not dealing with a common neutron star. Another clue could come from pulsars, which are rapidly rotating neutron stars emitting periodic radiation beams. If some pulsars present anomalous behaviors, like brightness drops or unstable rotation periods, it might be a sign their internal structure is more exotic, perhaps a mixture of neutrons and quarks. There's talk inclusive of hybrid stars, where only the deepest core would have free quarks, while the rest would still be neutron-dominated. Quark stars could also have dramatic effects on surrounding space. For example, if two collided, they might generate gamma-ray bursts even more intense than those we know. These collisions could leave specific signatures in gravitational waves we detect, different from neutron star mergers. The problem is we need very precise data to distinguish these scenarios. One of the most intriguing candidates is the object known as RX J1856.53754, detected in X-rays. It's small and extremely hot, but doesn't fit perfectly into neutron star models. Some researchers suggested it could be a quark star. Other examples include pulsars spinning at extreme speeds, close to the stability limit, where quark structure could explain their resistance. But so far, there's been no definitive confirmation. Interest in quark stars is also linked to particle physics. Understanding how they work can help answer fundamental questions about matter's nature. For example, is there a stable state called strange matter, formed by up, down, and strange quarks mixed? Some physicists believe so, and that quark stars could be composed of this matter type. If true, they would be even more stable than neutron stars, and could survive indefinitely without collapsing into black holes, even under extreme conditions. This idea leads to an even more curious scenario. What if pieces of strange matter could wander through space? In theory, tiny fragments of quark stars could spread throughout the universe after collisions, forming exotic particles called strangelets. If we ever find such particles on Earth or in high-energy experiments, this would be direct proof of these stars' existence. For now, everything remains in the hypothesis field, but advances in astronomical observations can change this picture. With the use of increasingly sensitive telescopes like James Webb and gravitational wave detectors, we might manage to identify indirect signs of quark stars. The simple fact that some measurements already don't match traditional models is evidence there might be something new waiting to be discovered. It's interesting to note how these stars fit into a kind of stellar collapse scale. First, we have white dwarfs sustained by electron pressure, then neutron stars sustained by neutron degeneracy pressure, and at the limit, black holes, where not even fundamental particles resist collapse. Quark stars would be between the last two, an intermediate step we perhaps haven't confirmed yet, but which physics predicts as possible. If we manage to prove they exist, this would mean the universe is capable of producing matter states we've only managed to simulate for fractions of seconds in terrestrial laboratories. It would be like finding a natural particle accelerator scattered throughout the cosmos, producing quark-gluon plasma on astronomical scale. And it's precisely this mixture of theory and mystery that makes the topic so fascinating. Perhaps some stars we classify as neutrons are actually quark stars. Perhaps we've already collected data from them, but haven't known how to interpret correctly. Or perhaps the first unequivocal detection is yet to come, the event that will definitively confirm these invisible colossi's existence. The fact we can theoretically predict their properties, calculate their density limits, and even speculate about their formation shows how far physics has advanced. But the fact they remain unconfirmed also reminds us how much we still have to discover. In the universe, the line between the possible and the real is often thinner than we imagine. Meanwhile, the search continues. Each new neutron star detected is analyzed not just for what it appears to be, but for what it might hide. And perhaps in some dataset already collected, or in the next gravitational wave detection, we'll find the definitive signature of these objects that would represent one more step in our understanding of matter's ultimate limits. Cannibal galaxies. When we look at the night sky, stars seem immobile, each occupying its fixed place in darkness. But on larger scales, at the galaxy level, the universe is much more dynamic and even violent. Galaxies aren't isolated entities. They interact, collide, and in many cases, devour each other. This process, known as galactic cannibalism, is one of the most important forms of cosmic growth. Instead of forming all at once, many galaxies increase in size over time by swallowing their smaller neighbors. The term cannibalism may sound dramatic, but it describes well what happens. A larger galaxy with a dominant gravitational field pulls and dismantles a smaller one in its vicinity. The devoured galaxy's stars don't disappear, but end up incorporated into the larger galaxy, spreading in new orbits. The result is slow but continuous growth that can transform medium galaxies into giants. This phenomenon isn't rare. Actually, it's a fundamental part of cosmic evolution. Astronomers believe practically all large galaxies we see today, including the Milky Way, grew through multiple cannibalism episodes. The universe, in this sense, is a competitive place, where galactic survival depends on who has more mass and gravity. A classic example is our own galaxy's relationship with satellite dwarf galaxies. Currently, we know the Milky Way is devouring small companion galaxies. The Sagittarius dwarf galaxy, for example, is in the process of being absorbed, its stars already spreading in streams, contouring the galactic halo. It's like observing a trail of cosmic crumbs, indicating the path of a meal already underway. The future also reserves even grander encounters. In about 4 billion years, the Milky Way should collide with Andromeda, our giant neighbor. It won't be a violent collision in the traditional sense, because stars within galaxies are too distant from each other to crash directly. But gravity will reshape them, both, mixing their stars and gases, until forming a new, even larger elliptical galaxy. In this process, we can say Andromeda and the Milky Way will devour each other in one of the greatest possible cosmic spectacles. The most interesting thing is we already have clear evidence of this type of event. Modern telescopes, like Hubble, have captured impressive images of merging galaxies, showing distorted spiral arms, stretched star tails, and regions of intense stellar formation. These encounters not only reorganize galaxies, but also trigger activity bursts in their cores, sometimes feeding supermassive black holes that fire radiation jets. Galactic cannibalism also helps explain some peculiar structures we see in the sky. Star streams that seem to flow around galaxies are often remains of smaller galaxies already devoured. It's like each of these streams were a cosmic scar, reminding us the larger galaxy grew at others' expense. This process can occur at different scales. Sometimes it's just a dwarf galaxy being slowly absorbed by a larger one. Other times, it's two giants colliding as equals. The result depends on how much mass and gas each carries. If there's much gas involved, merger can generate new starbirth explosions, creating galaxies full of bright regions. If there's little gas, merger tends to form calmer, elliptical galaxies, composed of older stars. In any case, it's a reminder that galaxies are living systems in constant transformation. The Milky Way's spiral shape, for example, might not last forever. After merger with Andromeda, it will probably become an elliptical galaxy, without the characteristic arms we see today in artistic representations. For future civilizations, the sky will have a completely different appearance. From a scientific standpoint, studying cannibal galaxies is essential for understanding universe history. Each merger leaves marks we can identify: star streams, changes in dark matter distribution, alterations in rotation speed. These clues allow reconstructing a galaxy's family tree, showing how many encounters it's had and how it grew over time. Dark matter's role in this process is also crucial. It's believed dark matter halos around galaxies are determinant for how mergers happen. These invisible halos guide orbits, absorb part of the energy, and help stabilize the final system. Without dark matter, many mergers might not result in cohesive galaxies, but in dispersed and chaotic systems. It's curious to think that, in a way, galactic cannibalism is a natural process of cosmic recycling. Smaller galaxies bring with them young stars, gas, and dust, which, when swallowed, feed new evolution phases of the larger galaxy. In some cases, this even activates central black holes, transforming them into quasars or active nuclei for a period. Thus, a cosmic meal can literally light up a galaxy's heart. Astronomers also study this phenomenon, seeking to understand giant elliptical galaxies' role in formation, which dominate galactic cluster centers. Many of these galaxies are the result of countless cannibalism episodes, each merger increasing their size and mass. When we look at one of these cosmic titans, we're seeing the product of billions of years of encounters and absorptions. Computer simulations are another powerful tool in this field. By modeling galaxy mergers, scientists can predict how structures will deform and how long it takes for a system to stabilize. These simulation results, when compared with real images, confirm galactic cannibalism is a central piece in cosmic evolution. For common observers, it might be difficult to imagine what happens during a merger. After all, talking about galaxy collisions gives the impression of total chaos. But in practice, most stars don't crash directly, since space within a galaxy is almost empty. What changes are orbits, gas distribution, and gravitational interactions. It's a silent and elegant spectacle, but with enormous consequences. On human scales, nothing happens quickly. A complete merger can take hundreds of millions of years. It's a slow, almost choreographed process where galaxies approach, distort, intertwine, and finally merge into a new system. For us, who only observe an instant of this dance, each image is like a frozen portrait of a much larger story. The Milky Way, therefore, isn't just a spectator of this process, but an active participant. It has already devoured smaller galaxies in the past, and will continue doing so in the future. Each star we see in the sky might, at some point, have come from a different galaxy, incorporated into ours over billions of years. In this sense, we all carry a little piece of this merger and cosmic cannibalism history. Thus, cannibal galaxies aren't rare exceptions, but the rule in universe evolution. They remind us the universe isn't static, but a scenario in constant transformation, where even gigantic structures are subject to change. And although these encounters happen on timescales far beyond human experience, understanding their functioning gives us a clearer portrait of how the universe builds and rebuilds itself. Blazars. Among all the universe's energetic phenomena, few are as impressive as blazars. They belong to a special class of galaxies called active galaxies, where the central nucleus isn't just a quiet supermassive black hole, but a functioning cosmic engine. These black holes, which can have millions or billions of times the sun's mass, attract enormous amounts of gas and dust around them. As this material falls into the accretion disk, it heats to absurd temperatures, emitting radiation across the entire spectrum. And in some cases, part of this energy is channeled into colossal jets, extending thousands or even millions of light years. What differentiates blazars from other active galaxies is a perspective detail. The jets produced by the central black hole are pointed almost directly at Earth. This creates an intensification effect called relativistic beaming, where radiation seems even brighter and more energetic due to the near light speed with which it's emitted. In other words, it's not that blazars are fundamentally different from other active nuclei, but that we have the luck or misfortune of looking directly into the barrel of their jets. These jets are composed of charged particles accelerated to relativistic velocities and emit radiation ranging from radio waves to gamma rays. This makes blazars extremely powerful energy sources, observable by multiple instruments in different spectrum ranges. In optical telescopes, they appear as bright points, but in high-energy detectors, they reveal their truly explosive nature. These objects' intensity is such that in some cases, they outshine the entire galaxy hosting them. Imagine an entire galaxy with hundreds of billions of stars, and yet the active nucleus, just a tiny fraction of its size, shines brighter than all stars combined. This is blazar's power, transforming a single point in the sky into one of the most energetic sources ever seen. From a historical perspective, blazars were an enigma for a long time. Initially, they were confused with variable stars, as they appeared as light sources changing brightness irregularly. Only with more detailed observations, especially in radio and gamma rays, was it realized these were distant galaxies with extremely active nuclei. The name blazar came from merging B-L Lacertae objects and quasars, two types of active nuclei that, when better understood, revealed they were essentially the same class, observed from different angles. Blazar's variability is one of their trademarks. They can change brightness on timescales ranging from days to just a few hours. This indicates emission regions are relatively small, comparable in size to the solar system itself. In some cases, gamma-ray radiation bursts were recorded in minutes, a clear sign that particle acceleration processes there are extremely efficient. Another fascinating aspect of blazars is polarization of the light emitted by blazars. This phenomenon happens because jets are immersed in intense magnetic fields, which align radiation in specific ways. By measuring polarization, astronomers can infer details about jet geometry and structure, something essential for understanding how they work. Blazars are also important for an additional reason. They're one of the few known sources of extremely high-energy neutrinos. In 2017, the IceCube telescope, located in Antarctica, detected a neutrino with exceptional energy and managed to trace its origin to a blazar called TXS 056 plus 056. It was the first time a direct connection was established between cosmic neutrinos and an identified astrophysical source. This opened a new window for so-called multi-messenger astronomy, which combines information from different particles and radiations to better understand cosmic phenomena. If we think in energy scales, blazars are at the top of the hierarchy. They not only emit more radiation than entire galaxies, but are also natural particle accelerators, capable of launching protons and electrons at energies surpassing anything we can reproduce in Earth laboratories. Some scientists believe they're responsible for part of the most energetic cosmic rays hitting our planet. Cosmology also benefits from blazars. Since they're visible at immense distances, they function as beacons illuminating the deep universe. By studying light coming from them, astronomers can investigate the intergalactic medium, measure absorption caused by cosmic dust, and even refine models about matter distribution in space. Thus, each observed blazar isn't just an isolated object, but a tool for probing the universe as a whole. Despite all this intensity, there's no direct risk to Earth. Blazars are at distances of billions of light-years, far beyond any practical threat. Still, the fact we can detect them so clearly, even from so far, is already an indicator of their extraordinary power. It's like seeing a candle lit on a remote island across the ocean, only multiplied by billions of times. Theoretically, there are still many questions about how exactly blazar jets form and maintain. We know the central black hole and its accretion disk play fundamental roles, but details of particle acceleration and jet collimation continue being investigated. Models involving intense magnetic fields and relativistic interactions offer good explanations, but the phenomenon's complexity makes it an active research field. Observations in multiple wavelengths are essential for unraveling these mysteries. Radio, optical, X-ray, and gamma-ray telescopes work together to monitor blazars, recording each variation and sudden explosion. This integrated approach allows assembling a more complete picture, almost like joining pieces of a puzzle, constantly changing. And it's precisely this unpredictability that keeps astronomers alert. You never know when a blazar will erupt, firing a radiation jet even more intense than normal. These sudden explosions not only challenge our models, but also offer unique opportunities to learn more about extreme physics governing these objects. From an imagination standpoint, blazars occupy a special place. They're like cosmic lighthouses, pointed directly at us, revealing universe violence and beauty on almost incomprehensible scales. Knowing we're in the line of fire of one of these jets, even billions of light-years away, is simultaneously frightening and fascinating. In the future, new instruments should further expand our knowledge. The Cherenkov Telescope Array Observatory, for example, will be capable of detecting extremely high-energy gamma radiation with unprecedented details. This should provide clearer answers about processes feeding blazars, and perhaps even reveal more surprises. The Great Nothing. If the universe is a tapestry of stars and galaxies scattered through space, the Great Nothing of Boötes is like a strange hole in this fabric. Located in the Boötes constellation, about 700 million light-years from Earth, it's one of the largest known regions almost empty of galaxies. To give an idea of scale, this void is about 330 million light-years in diameter. In comparative terms, if we placed the Milky Way at the center, other large galaxies would be so distant they'd seem like lost points in solitary vastness. The Great Nothing discovery happened in the 1980s, when astronomers mapped galaxy distribution across the sky. They expected to find a relatively uniform mesh, with clusters, filaments, and spaces between them. But when they reached this region, they noticed there were far fewer galaxies than predicted. It was like looking at a city from above and finding an entire neighborhood without lights, a silent space where there should be movement. The universe, on large scale, has a structure known as cosmic web. In it, galaxies organize into giant connected filaments, forming something like a web. Between filaments remain lower density regions called cosmic voids. The Great Nothing of Boötes is one of these voids, only on extreme scale, one of the largest absent structures ever identified. This void's size impresses even specialists. In such a large volume, millions of galaxies would be expected. However, astronomers found only a few hundred. This doesn't mean it's literally a completely empty space. There are isolated galaxies inside, but they're rare and distant from each other, like solitary houses amid an immense desert. This isolation raises several questions. How did these galaxies form there? Did they develop alone amid rarefaction, or were they trapped during the void's expansion? One possibility is that when the universe was forming, regions like this naturally became less populated because matter concentrated in filaments. Another is that dynamic processes over billions of years expelled part of matter from this area, expanding the void. For galaxies living in this environment, the story must be very different from those in denser regions. In clusters, galaxies constantly interact, collide, and exchange matter. Inside a void like Boötes, solitude is the rule. Interactions are rare, and each galaxy follows its path, practically isolated. This can influence their evolution, making them grow differently, perhaps with fewer stellar formation bursts or simpler structures. Observations also show the Great Nothing isn't completely homogeneous. Within it, there are small chains and galaxy clusters, almost like lost islands in an ocean. These concentrations are called substructures, and their study helps understand how gravity shapes even low-density regions. An important detail is that voids like Boötes aren't rare exceptions. The cosmos is dotted with them, but most are much smaller. What makes Boötes so special is its colossal scale, to the point of being nicknamed the Great Nothing. It serves as an extreme example of how matter distribution in the universe is irregular, with regions supercrowded with galaxies and others practically deserted. Studying this void is fundamental for testing our cosmology models. How voids form and evolve is directly linked to universe expansion and dark energy's role. By measuring these spaces' density and shape, scientists can compare real observations with computer simulations, checking if our theories about cosmos origin are correct. Another interesting point is that these voids can affect light crossing them. When radiation from distant galaxies passes through low-density regions, it suffers small alterations, an effect known as inverse weak gravitational lensing. This detail helps map matter distribution, including dark matter, which also influences void formation. Despite its immensity, the Great Nothing isn't dangerous nor represents a threat in itself. It's simply a region where gravity and matter organized unequally. But for astronomers, it's a fascinating study field because it shows the universe isn't uniform in all directions. There are places full of galaxies, and there are almost deserted places, reminding us cosmic history is made of contrasts. Some astronomers like comparing the Boötes void to the inside of a bubble. Imagine soap foam, where galaxy filaments would be bright walls, and voids would be dark spaces between them. The Great Nothing would be one of these bubbles, only hundreds of millions of light-years in diameter. This image helps visualize how the cosmos, on large scale, has patterns resembling almost organic structures. Of course, being such a large phenomenon, it also feeds imagination. There have been those who speculated cosmic voids could be signs of something not yet understood in physics, or even exotic events in the universe's beginning. Most of these ideas are highly speculative, but they show how the simple fact of existing such enormous and almost empty regions awakens curiosity beyond traditional science. For scientists, the challenge is obtaining increasingly detailed data about the Boötes void. New galaxy surveys using terrestrial and space telescopes are mapping cosmic distribution more precisely. Each new galaxy detected within the void helps refine models and understand how these regions evolve. The Boötes Void is also useful as contrast. By comparing galaxies living in voids with those in clusters, we can better understand how environment influences stellar formation, morphology, and even central black hole presence. It's almost like studying two different cities, a metropolis full of interactions, and an isolated village amid nothing. In a way, we can say the Great Nothing is a reminder of how heterogeneous the universe is. There's no single pattern of matter distribution. The universe is made of contrasts, dense regions full of light and activity, and deep voids where silence dominates. Each part tells a different story, and together they form the portrait of the large-scale universe. The Great Nothing of Boötes, therefore, isn't just an astronomical curiosity, but a key piece for understanding cosmic structure. It shows the universe is full of surprises, even in places where there seems to be nothing, and perhaps that's the most fascinating part. Discovering that even emptiness can be extraordinarily revealing about how the cosmos works. Dark energy. When we think of the universe, the first image that usually comes to mind is galaxies, stars, planets, and nebulae. But what sustains the cosmos, what really dictates its destiny, might be something we don't see, don't touch, and barely can describe. Dark energy. It's a concept that sounds almost poetic, but in practice it's one of modern science's greatest unknowns. This discovery story begins with a surprise. In the late 1990s, two independent groups of astronomers observed Type 1a supernovas, stellar explosions used as standard candles to measure cosmic distances. The expectation was confirming universe expansion was decelerating, as imagined since Einstein's times. But data showed the opposite. The universe was accelerating. Something invisible was pushing space to expand faster and faster. This result was shocking. Gravity, which pulls matter and tends to break expansion, seemed to be overcome by an opposing force. To explain the phenomenon, scientists coined the term dark energy, not because they knew exactly what it was, but because they needed a name for this mysterious, invisible, and dominant cosmic component. Today we know dark energy represents about 70% of the universe's entire content. Ordinary matter, that forming stars, planets, and people, corresponds to less than 5%. The rest is dark matter, which exerts gravity but doesn't emit light. In other words, most of the universe is composed of something we don't see and so far only know through effects it causes. But what exactly is dark energy? This is the question we still can't answer. One of the oldest hypotheses dates back to Einstein himself. In 1917, when applying his general relativity theory to the cosmos, he introduced the so-called cosmological constant, a mathematical term that could act as a kind of repulsive force, balancing gravity and keeping the universe static. Later, when it was discovered the universe was expanding, Einstein abandoned the idea, calling it his greatest mistake. Curiously, the same constant returned to consideration after discovering cosmic acceleration. If dark energy is really the cosmological constant, this would mean it's an intrinsic property of empty space. In other words, vacuum itself would have associated energy, pushing space to expand. This explanation is simple in conceptual terms, but raises enormous theoretical problems. Quantum physics predictions about vacuum energy are absurdly larger than the value observed in cosmology, generating a discrepancy we still don't know how to resolve. Another possibility is that dark energy isn't constant, but rather a dynamic form of energy associated with some still unknown fundamental field. This idea is called quintessence, referring to ancient philosophers' fifth element. In this scenario, dark energy could vary with time and space, shaping universe evolution in ways we can't yet predict exactly. Regardless of its nature, dark energy's impact is colossal. It's what dictates cosmic expansion rhythm. If its density remains constant or even increases, the universe will continue accelerating indefinitely, leading to a future known as Big Freeze, where galaxies become increasingly distant until disappearing beyond observable horizon. If, on the other hand, dark energy decreases or changes behavior, destiny might be different, from deceleration leading to collapse, the so-called Big Crunch, to more exotic scenarios like Big Rip, where accelerated expansion would tear apart even atoms. To investigate these mysteries, astronomers resort to various observational tools. One is large-scale galaxy mapping. By measuring how galaxies distribute and move away over time, it's possible to infer dark energy's influence. Another approach is observing cosmic background radiation, the Big Bang's echo, carrying fingerprints of expansion behavior in the universe's first instance. Recent missions like the Planck Satellite and Dark Energy Survey Project have already provided important clues, but we're still far from a definitive answer. The next step will be taken by new generation telescopes, like the Vera Rubin Observatory and Euclid Satellite, promising to map billions of galaxies with unprecedented details. These projects should refine our estimates about dark energy's density and nature. It's curious to note how the very idea of dark energy reflects science's humility before the unknown. Instead of pretending we understand everything, we give a provisional name to what we can't yet explain and continue investigating. In this sense, the term dark energy isn't a definition, but an invitation to exploration. This concept's impact goes beyond physics. It alters our philosophical vision of the universe. The notion that 70% of reality is composed of something invisible and mysterious reminds us what we know is just a minimal fraction of the whole. This challenges our intuition and expands scientific imagination limits. Some physicists also explore connections between dark energy and other fundamental theory areas. Is it linked to extra dimensions? Is it a manifestation of particles or fields we haven't detected yet? Or do our gravity equations need reformulating on cosmic scales? Each possibility opens an entire research field, and none has been completely ruled out so far. The fact is, despite all advances, dark energy continue being a black box. We know it's there, we know what it does, but we don't know what it is. This makes it simultaneously frustrating and fascinating. It's like investigating a crime where we have the clearest clues about the effect, but no concrete idea about the perpetrator. From a practical standpoint, there are no dark energy effects in our daily lives. It acts on gigantic scales in the space fabric between galaxies. But for cosmology, its presence is decisive. Without it, we wouldn't understand the present, nor could predict the universe's future. It's the missing piece in the cosmic puzzle. Meanwhile, new observations continue being made. Each distant supernova measured, each galaxy map updated, is an attempt to refine how we understand this invisible force. It's patient work, but one that has already revolutionized cosmology once and can do so again at any moment. Dark energy is therefore more than an abstract concept. It's the universe's destiny dictator, the invisible hand shaping cosmic expansion. And while we try to understand what it is, it continues working silently, determining whether our cosmic future will be eternal expansion, collapse, or something we haven't even imagined yet. The universe itself. When we talk about strange objects in the cosmos, we think of black holes, exotic stars, or merging galaxies. But perhaps we're overlooking the largest and most enigmatic of all, the universe itself. It's not just the stage where everything happens, but also an object with its own properties, which can be studied, measured, and compared with any other cosmic structure. And the more we look at it as a whole, the more we realize we still know very little. The first obvious question is, What's the universe's size? The answer, however frustrating it seems, is that we don't know. The observable universe has a radius of about 46 billion light-years, meaning we can detect light from objects that are, or were, at this distance. But this isn't the universe's real limit, just the horizon we can see. Beyond this edge, space might continue indefinitely. Some models suggest the universe might be finite, but without borders, like a sphere's surface in 4 dimensions. Others defend it's really infinite. For now, we have no way to verify. What we know is the universe is expanding. Since the Big Bang, about 13.8 billion years ago, space has been stretching in all directions. Distant galaxies aren't moving through space at high speed. It's space itself expanding, increasing distance between them. This process was initially detected by Edwin Hubble in the 1920s, and since then we've confirmed not just expansion, but also its acceleration, driven by dark energy. The universe isn't static, but dynamic, in constant change. Another intriguing aspect of the universe is its shape. Einstein's general relativity shows space can be curved, depending on the amount of energy and matter it contains. To measure this, cosmologists observe cosmic background radiation, the Big Bang's echo. Results suggest the universe is flat on large scale, meaning its geometry doesn't present large curvatures. But this flatness is so precise, it raises new questions. Why does the universe have exactly the right amount of energy and matter to seem so balanced? This question is known as the flatness problem. The universe's content also challenges intuition. Only a minimal fraction of it is composed of ordinary matter we know. Stars, planets, gases, and cosmic dust represent about 5% of the total. Another 25% corresponds to dark matter, which exerts gravity but doesn't emit light. And about 70% is dark energy, responsible for expansion acceleration. This means most of the universe is invisible and mysterious, known only through effects it produces. The object we call universe is actually dominated by the unknown. And it doesn't stop there. Besides measuring what composes the universe, scientists also ask about its topology. Is it simply unlimited in extension, or does it have a more complex shape like a torus, a space similar to a donut's surface but in larger dimensions? In this case, light could make complete loops, making us see multiple images of the same galaxy in different sky places. So far, no such evidence has been found, but the question remains open. The universe can also be described in terms of its history. Since the first seconds after the Big Bang, it went through dramatic phases: cosmic inflation, first atom formation, emergence of first stars and galaxies, and slow evolution to current structure. Each of these stages left observable marks. Cosmic background radiation shows the universe's state when it was only 380,000 years old. Galaxy distribution reveals how matter organized over billions of years. And more recent events, like galaxy mergers and supernova explosions, continue shaping the general picture. This historical approach reminds us the universe isn't just an object in space, but also in time. It has chronology, with a defined beginning and still uncertain future. Will it continue expanding forever? Will dark energy at some point change behavior and cause contraction? Or will space continue accelerating until diluting all matter at insurmountable distances? Each answer leads to completely different scenarios for cosmic destiny. Amidst all this, perhaps the greatest strangeness is the very idea that the universe can be treated as a physical object. When we talk about a star, we measure mass, size, composition. When we talk about the universe, we do something similar, calculate its density, expansion rate, content. But there's a crucial detail. We have no outside from which we can observe it completely. Everything we know comes from what's inside, from the viewpoint of observers who are part of this same universe. Another curious detail is the universe's age. Based on cosmic radiation and expansion rate measurements, we know it's about 13.8 billion years old, but some recent observations of extremely ancient galaxies raise doubts. Certain structures seem too mature for the cosmos's official age. If these results are confirmed, it might be necessary to adjust our understanding about first galaxy formation speed, or even reconsider part of current cosmological models. Besides questions about age, size, and composition, there's also the question about initial singularity. The Big Bang is frequently described as the beginning of everything, but we don't know exactly what happened at zero instant. Physics laws, as we know them, stop working when trying to describe scales smaller than the so-called Planck time, an unimaginably small fraction of second after beginning. The universe in this sense continues challenging us. We know quite a bit about its evolution after the Big Bang, but almost nothing about what happened before or during this event. From an observational standpoint, the universe is also the largest possible laboratory. It's in it we test particle physics theories, general relativity, thermodynamics, and even hypotheses about extra dimensions. Each discovery about its large-scale structure or invisible components serves as a natural experiment, impossible to reproduce in terrestrial laboratories. The cosmos is literally the largest study object ever conceived. And we can't forget the importance of large cosmic structures. The universe isn't homogeneous on small scale. It has filaments, voids, and superclusters, forming a gigantic cosmic web. This galaxy and dark matter network extends hundreds of millions of light years and is one of the most impressive patterns ever identified by astronomy. The universe, seen on broad scale, looks like a complex network, almost like neurons in a colossal brain. These structures formed from small quantum fluctuations in initial instants, amplified by expansion. It's fascinating to think tiny differences in primitive universe density gave rise to galaxies, stars, planets, and eventually us. The universe's strangeness isn't just in its vastness, but also in how microscopic detail influences macroscopic in incomparable scales. Another point still open is the possibility the universe isn't unique. Modern theories like eternal inflation suggest the Big Bang might have been just one among many. In this scenario, multiple universes would exist, each with its own physical laws. Although this is still in the speculative field, it shows how even the notion of the universe as object might be limited. Perhaps it's just part of something even larger. Even within what we can observe, the universe presents paradoxes. Cosmic background radiation uniformity, for example, indicates regions today separated by billions of light years were once in contact in the past. This only makes sense if we accept the idea of rapid inflation right after the Big Bang, expanding space at incredible speed. This theory solves various problems, but also raises new questions. What caused inflation? Why did it stop? And could it happen again? The most intriguing thing is that despite all these mysteries, the universe is comprehensible largely through relatively simple equations. General relativity describes cosmic gravity, quantum mechanics explains particle behavior, and together these models allow predicting a series of phenomena. But the great unification is still missing, a theory managing to reconcile both areas in a unique framework. The universe as an object remains incomplete in our understanding. Ultimately, talking about the universe as a strange object is recognizing it gathers all previous categories on a larger scale. It has black holes, exotic stars, cannibal galaxies, dark energy, and invisible matter. But beyond that, it has its own properties, expansion, age, geometry, composition. The universe is both the sum of everything and an entity with singular characteristics we are still trying to decipher. And while we continue mapping its structures, measuring its expansion, and speculating about its limits, the universe continues being, paradoxically, the closest and most distant of all mysteries. It's the absolute context, the maximum study object, and at the same time what most escapes full comprehension. The largest and strangest object in the cosmos might be precisely the entire cosmos.